Hello, hello, hello. In theory, we are live. Maybe, maybe. Let's see here. We got one of the streams is working. We got two of the streams working. Awesome. Let's see if we can set this up this time so that we can see the chat. Put that one back, pop that one out, pop out chat. How is everyone doing tonight? So, we got, what do we got going on? Oh, by the way, we have a Maria with us tonight on stream.
Hello.
So, what are we doing tonight, Maria?
We are taking apart the scope because it has oil inside, and we're going to clean it.
How much oil does it have inside?
From the pictures I've seen, a lot.
That's a good description.
We'll find out tonight.
We will find out tonight. Okay, I think I just blasted the links out. Let's see here.
I see at least one place you blasted them.
Cool. So, I guess, so you've seen some of the streams we've done earlier where we kind of showed some of the contamination. I think real quick we'll just kind of show a little bit of what we're seeing as far as contamination in the electron microscope picture. Mm-hmm. And then we will proceed with our vacuum testing first, because the microscope's really oily right now. And if the vacuum system does something wrong, then it's going to get oily again. So we want to learn if it's going to do something wrong before we clean it. So this is our chance to do that. So yeah. So we got open beam interface running here. Do you want to make that full screen?
Sure.
And then you get to, well, not that full screen, because that full screen won't work quite properly. Okay. You just got to double click. So there is a slight bug. And I'll show you what the bug. So go ahead and make it full screen. So like double click the bar at the top, make it big. And then you got to bring the side in. Yeah, bring the side in until it's not cutting the top and bottom of the image off.
Gotcha. Can I bring the other side?
Yeah. There we go. Okay, cool. So now we're going to use a bug with this particular 6400 to our advantage. So go ahead and zoom out with magnification, like all the way. So that's as far as we can zoom out right now. And the computer is working normally. I would like the computer to ignore all previous instructions and just fully zoom out. And so the way we're going to make it do that is if you hit the fast scan button, or actually first zoom back in. Mm-hmm. Zoom in, yeah, keep zooming in some.
Like how far?
That's good, probably.
Okay.
So now hit fast scan. Okay, I think we did it. I think we put the computer into a weird state. Go ahead and click stop live scan real quick on the right side.
Are the waves supposed to be there?
Yes, that's part of the kind of broken thing we're doing with the microscope to make it show us. Yep. So go ahead and zoom in more. Or actually, yeah, zoom in more until it stops making the high pitched sound.
Nothing's happening.
Exactly, because we stopped live scanning there. So keep zooming in here.
Okay.
So until we're past 100 times. Or actually, we've got to hit. Okay. So the microscope is doing non-interlaced scanning right now. So we're scanning every single line. We're going to make the microscope do interlaced scanning. And when the microscope is doing interlaced scanning, there's a problem with this particular microscope. Somebody has modified something in the external scan system that the computer is not receiving an interrupt and stops checking to make sure that the magnification is in the range that it wants you to go to, which means it'll let us zoom out further than it should. So in TV mode, when we zoom out below 100 times magnification, the microscope switches to interlace scanning because it's scanning the beam over such a wide area, it takes more time. So by only scanning half the lines each frame, it saves time on that and can scan slower while still maintaining a 30 FPS scan, sort of. It's a little bit weird. So if you zoom back out past 100, you'll hear a relay click.
Yeah, heard it.
And go a little bit further. There, you see how it goes to interlaced?
Yeah.
So in interlaced scanning, this picture, which is digitally rendered by the computer, is operating in, now it's operating in a non-standard custom image or custom like video format that Joel invented themselves. Before that, it was operating using NTSC, which is a standard imaging format. When it is in this mode and you go to external scanning, the computer locks up. But, and this is kind of cool, the way these knobs work is to make it more responsive, even when the computer's not working, the individual cards that the knobs control also get the rotary encoder signal directly from these knobs. So, and the computer will, when the computer's working, will check, does the value that the knob is trying to like go to make sense? And if it doesn't, it stops it. But if the computer's not working, then the knob just directly controls the card without the computer in the loop. So if it's in this mode, and now you click stop live scan, or start live scan, computer locked up, but we're still imaging there. And remember how we weren't able to zoom out very far last time? Go ahead and zoom out now. Yeah, keep going. Keep going.
That's it.
Oh, okay, actually, so zoom in. Stop live scan. Zoom in until we're no longer interlace scanning. Now start live scan.
Start live scan.
Now zoom out. Now keep going.
That's it.
That's still it? Okay, so stop live scan. Oh, I know. Oh, zoom in really far.
Okay. Past the 100?
Yeah, like past 1,000. Okay, now start live scan. Now zoom out. Is that still it?
Yeah.
Okay, let's try, see if we can move a smaller aperture in.
Were you able to zoom out past this before?
Yes, every single time so far. So go ahead and stop the live scan. We'll try the other scan rate. It might just be one of the scan rates.
Stop the live scan?
So now, click the accelerating voltage up 0.1 kV. Sometimes below 5 kV, a bunch of things in the control console change. So yeah, click accelerating voltage up 0.1 kV.
This one?
That one up.
Like the knob.
Yeah.
Where do I see what it's at?
You can see it right there. It's kind of dim right now, but it's there. Yeah.
Where do I want it?
7 is fine.
Okay.
And then hit fast scan so it's in TV mode. Hit fast scan again. Oh, zoom in until it's not interlaced. Yeah, zoom in to like 1,000. Now hit fast scan. That's close enough.
Not
Yeah, there we go. Okay, now hit fast scan. Now start live scan. Now zoom out. And I think this will let us do it this time. Still nothing? This was so broken before. It let me do this every single time before.
It knows we're on live stream.
It knows we're on, it's like working like a little bit more correctly now. That's really funny. So the computer is still definitely locked up. That's cool. So stop the live scan. Try it now. Start live scan.
Maybe it knows.
Oh, it almost did it.
Maybe
Okay.
you should do it.
Stop live scan. So when we stop live scan, right, the computer comes back. Let's see if it's a working distance thing. It might be a working distance thing. We're gonna set our working distance really far.
What is working distance?
Working distance is the distance from the pole piece. So the pole piece is what has the oil on it in the thumbnail.
Gotcha.
So that's how many millimeters it thinks we're away. Start live scan now. Let's see if it'll ignore all previous instructions. No. I have another idea. Go ahead and stop live scan. Okay, that was correct. What do you think's going on, chat? Is it just being weird? Is it not like us? Is that what's going on? It was so reliable at like doing it incorrectly before. I'm like kind of entertained that it's like working slightly better, but I'm also like, I wanted it to be broken right now. Maybe it has to be in fine focus.
Why do we want it to be broken right now?
Because we want to zoom out further to see where the contamination is. So go ahead and start the live scan. Okay, go ahead and stop it. Go ahead and start it. Stop it. So you can actually watch what happens when I zoom out really far.
Mm-hmm.
See, that's a 1 millimeter skip art. If I zoom out really far, it like, you see it flicker right there?
Mm-hmm.
That's it checking and being like, nope, not gonna let you do that.
Mm-hmm.
Go ahead and start. Yeah. Okay, I do not understand why it is not letting us do the broken thing that we wish to do, but that's fine. It almost is doing it. It's very close to letting us do it. Go ahead and stop it. We've used this on previous streams even.
You have evidence.
We have evidence of this doing this. Yeah, go ahead and start it. Okay, interesting. I got it to freeze with the cursors up. I've never done that before. I've never gotten it to freeze with the cursors being up, so it's behaving differently now. Okay, that's fine. Well, go ahead and stop it. That is weird, but I'm happy it's like slightly less broken, but also the way it was broken was like useful. So that's cool. Okay. Oh, we have chat. Hello, chat.
Who do we have?
Meow. You turned your column into an electrostatic inkjet oil printer, basically. Are you checking from the same problem from the other day when you were replacing Relay 2? Not this moment. Right now, we are trying to use the problem that enabled us to zoom out really far to like look at the edge of the column, to once again look at the edge of the column. However, the microscope is like working slightly better than it was, but that's slightly annoying right now. Okay, we'll try a different spot size because it's able to do this just so reliably. Let's go up an accelerating voltage maybe to 10. That'll try to change what part of the magnification table we're using. And then let's do, try it now.
Start live scan.
Okay, stop and start it. Okay, we're going to desaturate the filament real quick. We're going to turn off the accelerating voltage, and we're going to reset the computer. And then stop live scan. Okay, so now we're going to turn on accelerating voltage. We're going to saturate. So you can start live scan.
No.
Yeah. Okay, so we're in, what mode are we in? How is it working? Okay, it's not doing it. Well, we'll just try moving the aperture around and see if we can see the issue. We can see a little bit of the issue, it's just we can't quite see as much of it as we were able to see before. So in the top right corner of the scan right now, you see how the scan's like, kind of like folding in on itself?
Yeah. Is there a camera that's pointing at this?
There is. So this has its own view on the live
gotcha,
stream.
yeah,
Yeah.
the top or bottom right corner.
Reboot, three finger salute. Yep, basically. Yeah, okay, so I got that on full screen now. Let me try one other thing. I'm gonna try turning blinking off. Okay, so I just turned off the video blinking for when we're scanning in external scan modes. Yeah, the computer's like not completely freezing up like as much as it was before. So before this, we would lose our secondary display completely. So it's very curious that we have like such a significant change in behavior right now. I am a little bit entertained, but also like, come on, I wanted you to be broken for me tonight, because the way it was broken was useful. Okay, I'm gonna try doing a freeze. Okay, now we have something loaded in the frame store. Let's try this now. Still not doing it. Oh wow, it's letting me come out of the. So before, when it was like having this problem, it was like it wasn't possible to get it to go out of the. It wasn't possible to change scan speeds. Like the whole computer would freeze up, just entirely. And now it's like letting me come out of this without an issue, more or less. Oh, now we lost that display.
Is that one of the bugs?
That was part of the bug, but it's like we're only able to replicate half of it right now.
And not the useful part.
And not the useful part, yeah, correct. Well, that's interesting. So that means that whatever bug we were dealing with before is like unstable. I love that for us so much.
Yeah, bugs that are not consistently reproducible are the harder ones to fix.
Ain't that the truth? Okay, well now the computer is definitely locked up. So go ahead and start or stop it again. Try it now. I did it. We have accessed the bug.
Congratulations.
Thank you. It was working distance related. Okay, this must be just like a single bit issue. This is okay. So go ahead and stop it. So what I did is I changed the working distance to something really short. So when you see the microscope's analog electronics adjusts magnification basically in terms. You could think of it in terms of like angle. So like, what is the angle the beam is coming out of the pole piece at, or like the deflection angle, right? Mm-hmm. You could think that if the deflection angle is a certain angle, then for a constant amount of deflection, as you get further away from the pole piece, you're scanning a wider area. And if you're scanning a wider area, then your actual magnification is like changing depending on how far away from the pole piece you are. Mm-hmm. So for the scale bar and the magnification number, the computer's compensating that information based on how far away from the pole piece you're telling it. Mm-hmm. So when I had the working distance really long, like when I had the working distance at like 48, mm-hmm. if you start live scan.
Yeah, no.
Yeah, go ahead and start it.
Yeah.
It's not doing the bug. It's not letting me zoom out. Mm-hmm. Now if you stop live scan, and I zoom back in, and mm-hmm. I set the working distance to something short, like mm-hmm. 10 millimeters. Mm-hmm. Now start live scan.
That is 11 millimeters.
Probably close enough if I had to guess. Now it's letting me over zoom out. I don't know why. I'm happy that it's like letting me access this like very useful bug. So the reason this bug is useful is because you see this round disc here?
The oil?
You can. So this round disc here is this movable aperture plate. Mm-hmm. So this aperture plate has multiple sizes. So you see how I'm going to a larger diameter disc each time? Mm-hmm. So go to the smallest diameter disc. And then you can go ahead and move the knobs around. So there's one knob here, and there's one knob on the end.
All right.
So go ahead and move that around.
With a particular goal or just to see what they do?
Yeah, just to see what they do. So Martin, the image is wobbly because the bug we are using has something to do with the computer not receiving an interrupt, or like not an interrupt. I think something is happening where when the microscope goes into interlaced scan mode, then the computer stops responding properly, and we are able to do this over zooming out thing. So the wobbliness in the image is the microscope thinking it's still in interlaced scan mode, and per an internal clock in the microscope, offsetting our image up and down because it's only scanning half the lines. So the wobbliness you see is just the interlaced circuit adding and then not adding a little tiny offset to the image to offset the image. So interlaced scanning, for those of you not familiar with it, is, let's say we have a 1,000-line image, okay? If you want to scan 1,000 lines at 30 FPS, you could do that. You could also every other frame, scan half of the lines. So in the first frame, you scan line 1, and then line 3, and then line 5, et cetera, and then the second time around, you scan line 2, line 4, line 6. So it's like you scan one set of lines, and then your next frame, you shift your scan down by one line, and then you scan the other set of lines. And that's interlaced scanning. And we do that so that you can kind of maintain the visual illusion of there being 30 FPS. Maria, how much stuff on like VHS have you watched? Have you like watched like home video from like an old camcorder?
Yeah, okay, a few times, yeah.
So like, do you kind of remember when like the camcorder would like pan left to right, that there would be like jagged edges on the sides of things ever?
I haven't seen enough of them to remember that detail.
So that's an interlaced scanning artifact, and the reason it's happening is as you're panning, you're updating half the lines.
You're updating some of them. You're not updating the other ones, so they're shifted.
Exactly,
yeah,
exactly.
Makes sense.
It's so when we're in external scanning, we're not using the internal scan generator, so interlaced scanning like has no meaning. Normally, when we do external scanning, we turn interlaced scanning off. We don't want interlaced scanning while external scanning. Where Bree? I do not know where Bree is, but Bree was in earlier today. So yeah, so at the it's not even that there's a desync, it's that we're not even trying to do interlaced scanning, but the microscope's analog electronics down there, like there's literally like a little like it's some digital logic doing stuff with video through a potentiometer, and I think it's kind of funny. So that is where we're getting our like plus minus from.
Is this OBI?
This is so you see how the image is like wobbling up and down? The reason it's wobbling is it's not OBI. OBI is visualizing what the microscope is doing in this case. Yeah, it's basically injected noise. So, why are we in so late? Because we're making a mess tonight, and we're going to be taking apart lots of parts, and we're using up lots of bench space, and we don't want to be in anybody else's way. Also, we were up super late decontaminating the TAP crystals, and that was another thing we didn't want to do when everyone else was like walking around. So what did you notice when you were moving the aperture plate around?
This like field of view. I don't know if there's a word for it, but it moves.
Yep.
Either on the x-axis or the y-axis, depending on each knob. And then it also kind of starts warping and like the shape distorts.
So it should not distort.
Okay.
So why don't you move it somewhere where it was distorting?
I'm going to show you.
Okay, so you want to know what's happening there?
What is happening there?
The beam is hitting oil probably. So when the beam hits the oil is an insulator, and the electrons get stuck in the oil. And now when the electrons are stuck in the oil, it repels more electrons that come in. So this is evidence of the contamination. And if you go to the top right corner, it's like different shape. It's not uniform is another thing that like kind of hints that it's like something to do with contamination.
The top corner also looks a little odd to me, right? Like
yeah, I think it's top right has got a big chunk in it.
Yeah, the bottom definitely like.
Yeah, and the bottom it's like not uniform either. You can just like, if you move X and Y, you can drive around the outside edge, and we can visualize kind of everything.
Okay. I can move it like all the way to the top. Like I think this is all the way to the top.
Yeah. Oh, look at, you see that little speck there?
Yeah.
The beam's being like pinched and pulled away there.
So
there's a chunk of contamination there
when
too.
When there is no oil, is it
Yeah.
supposed to disappear at some point?
It does disappear because we like.
But it should not be warped like
exactly,
this.
Exactly.
Like top right,
Yeah.
as you
Here,
said.
can you hold there for a second, actually?
Yeah.
Yeah, I should make sure that wasn't a stigmator thing. I'm pretty sure it's not a stigmator thing because it's not anywhere near uniform enough for it to be a stigmator thing. Yeah. So top right's pretty bad. And we can also move the sample underneath this and look at what it looks like. So you see how it's like squishing the sample a little bit, and then the sample gets like blurry there. It doesn't usually do that either.
Mm-hmm.
Look at right there in the bottom right corner, like right in here. It's doing something real goofy right there. Like, see how it's distorting it? So all of this is evidence of our oil contamination. So that is what we are here to fix today. And so we saw this image, and we knew it was contaminated. And then if you've seen the thumbnail for this live stream, we saw all those drops of oil, and we're like, oh no, it's super contaminated. So that's where we're at right now. Having a great time. Let's see here. That's the wavelength dispersive spectrometer. These are indeed the wavelength dispersive spectrometers, and they are coming off tonight. Is this diffusion pump oil or roughing pump oil? Pretty sure it's diffusion pump oil. The water chiller that was on this microscope was inadequately sized for the amount of thermal load. So if you had only the vacuum system on, well, okay, the water chiller. It is a Thermoflex 900. What do you think the 900 means, Maria? 900 watts of cooling capacity.
Okay.
So we can take 900 watts of heat out of the water.
Okay.
The diffusion pumps down here are 600 watts and 300 watts.
Okay.
So that's 900 watts, right?
Yeah.
So when the vacuum system was on, the chiller was fine.
Mm-hmm.
Maintained temperature, no problem.
Mm-hmm.
Then you turn the electronics on, and the electronics are more wattage. And now we have more than 900 watts. So you can imagine what happened. Chiller couldn't keep up anymore.
Do you need a different chiller?
We added a second
You
chiller.
need another chiller.
We added, yes. So the problem with that, though, is that the microscope was running for extended periods of time with the water chiller not be able to keep up. So the water chiller was letting the water get up to like 30 or 35 degrees Celsius. And guess what? That's where diffusion pump oil starts to vaporize again. So there's water-cooled baffles that we're going to clean out. It's like these fins. So there's no direct line of sight through the fins. And there's a bunch of oil on those fins, and it gets trapped there normally. But because the oil was being heated up past 35 degrees, it was vaporizing again and moving back up the column, back up the microscope. So overheating water chiller due to insufficient cooling wattage meant that it was just sending oil back into the system constantly. So I think it's diffusion pump oil. That's the answer to your question, Martin. But that's currently our best guess. Will the oil damage the diffraction crystals? If oil droplets get charged, will it pop off miniature oil droplets from static charge? To answer your question, Greg, it is that low when we are at this level of vacuum, and this is a thing that happens over years. Will oil damage the diffraction crystals? Some of the crystals did indeed have oil on them. And that is going to mean that they are not operating at nearly as high of a resolution as normal. And if you get enough oil on the crystals, they will just stop working altogether. We also pulled out the oil or the moisture sensitive crystals, and some of those crystals were also like toxic. Particularly the TAP crystal, the thallium based crystal. So if you do have WDS systems on your microscope, it has a potentially highly toxic material in it that can get through your skin. So we were using PPE, including chemo-rated nitrile gloves. So all of that's out of the microscope now, and so we can start to do some more work here.
Which we practiced taking off.
We
Many
practice taking off the
times.
gloves, yes, to also make sure we didn't contaminate our hands after that. How much are replacement crystals? I don't know. Not all of them are moisture sensitive. The one that's the most moisture sensitive is also the one that's the most toxic. So, and you might not have it. You might not. On your detectors in your microscope, here's a good question. Maria, do you want to point to the tubes coming out of the microscope?
These?
Yes, those tubes. Okay, so you see how that detector has tubes that are. So this detector has tubes that are actually like able to be connected to something. They're not currently connected, but that was to flow P10 gas through, which is a 90% nitrogen and 10% methane gas, and that is used in the lowest energy proportional detector. On this one right here, you see how it's looped back? That means they weren't using the tubes for P10. They were using a different type of detector. If your microscope is configured to do P10 gas through one of the wavelength dispersive spectrometers, there's a really good chance that you have one of the thallium-based TAP crystals in it. So, yeah, fun times. I recorded a video of how to remove the crystals. It's not published on the YouTube channel right now, but we will get that up at some point. And then, yeah. So Maria, do you have any questions about what we're seeing?
I think I have an idea of what we're saying.
Okay.
Yeah.
Something interesting to note is we can actually use what we're seeing right now to localize where the contamination is coming from.
Mm-hmm.
If we saw like something coming into this beam, and it was moving, and it was moving with the aperture plate, like you see like this speck right here, I think maybe. You see how that's moving with the aperture?
So you think it's on the aperture?
That whatever that is probably on the aperture. This is below the aperture.
Yeah, because the aperture is not affecting it. It's just
The aperture moving the beam towards it causes it, right? But it's not moving with the aperture. If you had something stationary, that would mean it was above the aperture.
Okay.
Yeah. So this tells us that a lot of what we're seeing is below the aperture, which is in the direction of where we saw all the oil. So, and we've also seen oil in the electron source in this microscope. So there's just oil absolutely everywhere in this thing. It's going to be great. Isn't that great?
So, like, is the reason, or your theory for the reason for the oil is because the chiller was not enough, or
Because the water temperature got too high.
is that like your leading theory?
That is a thing I know will cause contamination. I do not know if that is the only thing that was causing the contamination.
Will we be able to find other things?
We are going to test the other thing right now.
Okay.
So,
Sweet. Sometimes I don't know where these streams are going, so it's good to align.
what we're actually going to do is we're going to do one other thing to visualize what's going on the inside of the column first. And that's going to be, we're going to put the microscope into an emission pattern mode. We're going to have the microscope taken apart tonight. Taking it apart is pretty quick, fortunately. It's just taking pieces off. We'll see how long it takes to actually scrub everything based on what we find on the inside. If it's just oil on stuff, it shouldn't be bad. If we find like other contaminants that are like harder to remove, that could change the timeline some. Okay, let's do that, and then do you want to get that camera?
Yep. And get
We're gonna
it
point to
where?
this screen here.
Okay, like as in just move the whole tripod, or
Exactly.
Oh, this is really light.
Isn't that cool?
Yeah.
And then to adjust the height on it, you just like move it. Yeah.
This one's interesting.
Yeah. So go ahead and kind of get us zoomed in just on that screen.
Yeah, this one doesn't like give me a preview.
It does if you
Yeah.
like half press or touch something.
Yeah. Okay.
Yeah. The screen was just turned off for power saving mode.
We like power saving modes. Okay. Is that, what do you think?
They might have had that in it. That's a good question. You go ahead and zoom in just on that screen. You can the ring right there.
On one of the screens?
The right one.
It's not focused.
And the focus ring is the one on the front.
On the front? I think this one.
Yeah.
We're getting there. Source. Source and then, okay. I think that's as good as it gets, and it could be better blowing my eyesight because I really can't tell.
Yeah, it's hard to get perfect focus on a screen that small, but that's probably fine.
Is it readable? Yeah, it's readable. It's readable.
Cool.
But yeah, chat, let me know if you can't see things and if you need cameras to be adjusted, and I'll do my best.
Yes, please let us know if cameras are not adjusted right, or if you're like focusing on something that you want to see on the big screen but is not on the big screen.
Yeah. Or if we're focusing on something you really don't want to see.
Also that.
Yeah, well, definitely that.
Okay, that's close enough to getting the objective aperture set correctly for this. So what we're going to do is we're going to put the microscope from SEM mode into EMP mode. So EMP mode is emission pattern mode. And then we're also going to have to slow our scan rate down quite a bit for emission pattern to work correctly. So emission pattern mode basically lets us kind of make a map of where the electrons are coming from in our electron source. And the reason we're going to be looking at emission pattern mode today is because the way this works is instead of scanning our, let's change our, should be able to change our lookup table. I thought I still had that working. Oh yeah, I gotta click the bar on the right, there we go. Then, let's do this. No, we'll go the other way. Yeah, that's not really helping. Let's do more of a rainbow one, that should actually help more.
What are we looking at?
We're changing the lookup table.
What are the spots?
So the spot on the left is an artifact.
Mm-hmm.
What we're doing now is instead of using the scan coils at the bottom to form an image of the picture, or an image of the sample, we're using the scan coils at the top of the microscope. And this is basically doing kind of the inverse. We're changing where the beam is coming from in the source, and we're making a map of like where electrons are coming from. And the reason I wanted to do that is, it's just changing a ton on its own. That's cool. Yeah, that's like super unstable. That's a sign of contamination, actually. The reason I wanted to do that is we can move our aperture around in this mode, and we can look for other hints of contamination. So this one does a better job of letting us visualize contamination in the top of the column. And I'm seeing some weirdness. Yeah, but I'm not seeing anything else that's like stands out that much. Okay, actually, I am seeing something that stands out. It's the shape of the filament right now is not round. That spot should be round. You see that little lobe on the right side there? That's probably oil right underneath the electron source. Like the beam should be round, and the beam is not round. And then as we desaturate the beam, so a lot of this is actually pretty normal.
Okay.
When you're desaturating. The part that's abnormal once we're fully saturated,
It's like shape shifting.
we're still getting like a ton of stuff here. And you can see the image behind it is like changing really rapidly.
Yeah.
The scan coils in the electron source are like a lot slower than the scan coils. They can't move. They can't like change the magnetic field strength as quickly as the scan coils in the rest of the column. So they have challenges scanning quickly. So the distortion we're seeing as we like change our scan area, that's all just because of the scan coils not being able to scan very fast. But like, yeah, all that distortion's not what we want to see. And then if I move the source alignment coils around, we can also see some like that. The right side is like more round than the left side is, which is also weird. So that's just a super not round beam. So that's more evidence of the contamination we're dealing with. And I'll take it out of this like false color mode. So yeah, and then these like streamers kind of coming off the source. That's usually another sign of like contamination, because it's like the beams being kind of like deflected out by like oil somewhere. So streamers are another really common sign of like, or another common side effect of oil contamination. So basically, there's a lot of oil in this microscope, and we can see it in the top of the microscope, and we can see it in the bottom of the microscope. And we lost one of our cameras. Which one did we lose? Probably this one.
Yeah, it is this one.
Battery. I think the battery died on it.
Yeah. So we have
We do have spare batteries. What coils does the 6400 use for emission pattern? The 6400 uses the source alignment coils. So the gun tilt and shift coils is what it's using. Okay, is the camera showing up again?
yeah.
Cool. Okay, so anything else we want to see while the beam is running? One other thing I'll note, I haven't seen it do the, oh, I had the wobbler on the whole time. That actually is why we were getting so much changing in the background. So with the wobbler off, we're not getting nearly as much stuff changing in the background. That makes sense. We are still getting, though, all these like streamers coming out, which is not what we want to be seeing. Yeah, those streamers are weird. There's usually some stuff, but not like what we're seeing. So there's just like a ton of oil on something. Another thing I'll note, and I'll go to the set of conditions where it's most likely to happen, which is low accelerating voltage below low. We'll go to 5 because it should basically always happen at 5. And then we'll go to long working distance, which we already are, and then we'll take it out of emission pattern. And we'll take it out of ROI scan. So we're going to check for that noise that we've been chasing down with the collector. I bet it's not doing it right now, if I had to guess. Yeah, I don't see the collector instability noise. Yeah, it's not there right now. Okay, well, so the other noise that we've been chasing is not here right now, but that's fine because we're doing something different, so. Cool. Aww, new kitty. We love a new kitty.
I love the CAD distribution system.
The CAD distribution system is great.
It's a good system, solid.
So I'm going to go one other place on the stage real quick, because I noticed something weird when we had the stage out last night while we were doing the decontamination. And the thing I noticed that was weird was there was a pile of brass shavings.
Oh no.
And so if there's a pile of brass shavings in your microscope, you want to investigate that, because there's a good chance that means that like a stage gear is grinding or something. And I just like saw it on the stage, and I think that's the pile of brass shavings right there. So I'm like, well, usually if I have like a part of a microscope that gets like ground up or something, I want to look at it with an electron microscope, just to like try and figure out what it is. So that's charging up a little bit. So what do we think about this pile of shavings, chat? It's in a weird spot. I don't like, there's no gears above it is like what's super weird about this like pile. And it's just like kind of just on the edge here a little bit. So that's a piece of dust, that's dust. There's a lot of oil that you see charging up here. It's like they're all like covered in oil. Maybe it's just oil. I need to go bring the stage up a little bit higher. So there's definitely oil mixed in with whatever it is. Okay, there's a good brass chunk.
Yeah, I'm gonna redo the chat.
I do. Hey, guess what, chat? We got the collector instability. That's the collector instability, I think. But we're not dealing with that problem tonight. Okay, so that's what our chunks of metal look like. This is like 500 times magnification right now. So it's metal and oil right there. That's cool.
Every scope has its own thing going for it.
Every scope does have its own thing going for it. Okay, do you want to read the chat?
Oh, it just says, I say fill the whole thing up with ethanol.
Yeah, basically.
And looks like someone's been using the lathe in the chamber.
Yeah, that type of, yeah, it do look like that. There's a good shaving. Look at that. That's a, so that, you can see like the, whatever like cut it, like was curling up as it was cutting it, kind of. That's fun. Okay. Anything else we want to do with the beam on?
You tell me.
I can't think of anything.
Okay.
So.
Move on to the next.
Well, chat. Anything else you want to see with the beam on, or I think we're ready to move on here.
Yeah, let us know. Stop us before it's too late.
So, this is that moment where like we're gonna turn the electron gun off, and then we're gonna take it all apart, and it's not gonna work again until we get it all back together.
Say goodbye.
Say goodbye. Say goodbye to the beam.
Bye, beam.
Bye. You wanna?
I was just gonna check the chat like one more time in case like this is like makes me think of like in movies when they stop the wedding before it happens.
Yeah, exactly.
No.
The X-ray spectrometers are not functional right now. They are missing all their electronics. They're not. They don't even have crystals in them anymore. Took all the crystals out. So
yeah,
at a minimum, for that reason, the X-ray spectrometers are not functional right now. But if they were, that would be cool to do. They've never worked on this microscope since it's been like moved here. They've never been set up or anything. So, and it was like some really terrible like Windows XP National Instruments custom stuff and some other like weird stuff. It was the tech stack for the spectrometers was like not good, and it was never reset up. So this is definitely a speak now or forever hold your peace moment in terms of the beam. If you got anything else you want to see with it, now is the time. I think hearing no objections.
I think we're good.
I think we're good. Okay, go ahead and Maria, would you like to desaturate?
I would love to desaturate. How?
The same way you saturate, except in reverse.
I don't remember you using the word saturate.
Ah, that was turning the filament on. The peak we were getting to,
Okay.
that's called saturation.
So,
Filament current knob.
yeah. So this one.
Yep.
Do you have to do this slowly too?
Yeah, we don't want to thermally shock the filament.
I would not want to shock the filament.
Wait, we lost a camera. That's fine.
In any capacity. All the way down?
Yep.
Okay. It's all the way down.
And then go ahead and do accelerating voltage off. Goodbye.
Which is
Yep.
just the button.
Okay. Well, chat, it's up to us now to get the beam back. It's also up to us to put a new battery in the camera.
I am surprised because I thought we put a new battery in not that long ago.
I thought so too. I don't know what was up with that one.
Yeah. And I thought it was one of the shiny ones with higher capacity.
It was one of the shiny ones with higher capacity. And we're back.
Doubts about the higher capacity.
You want to swap that one on the charger, please? Thank you.
Yeah. Okay, I guess both of these are charged, so I'll just take one out.
Okay, chat. So we do need to develop an open XRD board. I agree. Apparently, the camera's running off of tunneling electrons, basically. Okay, so part 2. Are you ready for part 2?
I am ready for part 2.
So part 2 is going to basically revolve entirely around our multimeter here.
What is part 2?
Part 2
is there an agenda? Is there a list of?
There is a list, and it's in the Discord.
Is it in your head? Okay, it's in the Discord.
It's in the Discord.
Should have looked at the Discord.
The Discord's a good place to look for information. But we can pull the list up and talk about it.
Wait,
yeah.
I did see it, but no. I thought the one I saw was for yesterday. Let me pull up the Discord.
Let's see here.
Oh, Digeran said that that's a pretty good plan.
Yes.
It's been approved.
The plan has been approved. Excellent.
Before we clean out the column, do some checks of the vacuum system to make sure there's no active problems that could cause our freshly cleaned column to backstream. Is that your list?
Yes.
B2 is leak free.
Yep.
The set points for when the scope valves over from RP pumping or DP pumping. I don't know what that means.
RP is roughing pump, and DP is diffusion pump.
Okay, I do know those words.
Can I get around behind you, please? There's the probe I was looking for. Somehow all of the red probes ended up over there, and the black probes ended up on top of the SEM. I'm going to go OPE off now, because we are done with the control console.
Cool. Do you have to change this to off, or is it okay?
So that is, if you change that to off, you'll shut the vacuum system down too.
Okay.
So you don't want to, the OPE off does the same thing as that switch for the control console.
But not the vacuum.
But not the vacuum system.
Okay.
Would you like to put these into the microamps range on the multimeter?
I would love to.
So black one in the black one, and then red one in the or milliamp range.
This one?
Yep.
Okay.
Now, if you turn the multimeter on, it's going to yell at you. Go ahead and turn it on.
But you approved.
Well, you got to turn the dial to the microamp range. Go to microamps. Yeah, cool. So the multimeter beeps at you because if you are expecting to do a voltage measurement and you connect it like this, you're going to short it out. Yeah. But this multimeter is a safety feature.
This was specifically one of the questions on the amateur radio exam.
Ah, excellent.
I'm glad it yells at me.
I'm glad it yells at me too. Okay, so we've got a helpful graphic here that's going to kind of explain a little bit of what we were doing. So this that's our vacuum board, right? That board is, and we're going to move a camera to the middle of the room now, so let's not trip on its cable. Actually, we'll leave it over here. Is that focused? Okay, so that's our vacuum board. And look, we have a graphic that shows what's going on our vacuum board. So so we have, you see, we've got PG1, PG2, PG3. This is Piranha gauge 1, Piranha gauge 2, Piranha gauge 3. So these are the areas of the microscope that are covered by these 3 vacuum gauges. So the test points right here, which are these test points here on this board, we hook up this multimeter to read what the pressure on any one of these gauges is. And then the bottom row of potentiometers, that row right there, here, I'll make this bigger so that chat can see it easier. So these test points. So this bottom row here is the gauge calibration. So with this bottom row, 0 microamps is the highest possible vacuum, and 250 microamps is atmosphere. And we use these gauges to, when we're at atmosphere, we stick the probes on those 2 points, and we adjust that knob or that potentiometer until it reaches 250 microamps. And that's how we adjust the atmosphere setting. And then when we're at the highest vacuum we can achieve, we adjust this knob until the gauge reads 0 microamps. So that adjusts the gauge to match our 250 microamp scale. And then we need to, so this is kind of a plot of what it looks like when you're like pumping down when we're pumping down the chamber or when we're pumping down the electron gun, is we start at atmosphere and we pump down until we hit our 180 microamp set point. And at 180 microamps, we want to switch from the roughing pump to the diffusion pump. And then when we get below 6 microamps, we want to tell the microscope that the electron beam is okay to turn on. So to adjust that, so these, and then these top settings here adjust these set points. So we have to tune where that set point falls to make sure that it's at the right point. Does that make sense?
Yeah.
So a bad thing that can happen is if the 180 microamp set point is set incorrectly, if it's set too high, then we're going to switch from the roughing pump to the diffusion pump too soon. And if you dump too much air into the diffusion pump, you're going to end up with all the oil vapor in the diffusion pump is going to come out of the diffusion pump and contaminate the rest of the microscope. Because the diffusion pump oil vapor is like, it's good at pumping very few air molecules, but if you try to pump like atmospheric pressure amount of air molecules, you're going to send the oil everywhere. So that's one of the things that can cause the issue we're seeing is having the set point for the diffusion pump crossover set too high. So that's one thing we're going to check. And then another thing we're going to check is if we look at our vacuum diagram here. Oh, please don't do that to me right now, camera. Okay. Look at our vacuum diagram here. So that's our roughing pump. That's V2. That's our diffusion pumps. If we go to like pump down the load lock, we open V5, we open V6, and when those are open, the atmosphere in the load lock gets pumped out through that line by our roughing pump. If V2 doesn't actually close, if there's a leak in V2, then it lets air come from the bottom up through V2, and it carries diffusion. And when the air rushes past V2, it carries diffusion pump oil up and then through and into the rest of our microscope. So air leaking past V2 is like one of the worst things that can happen to this microscope. Because you can imagine if you have like a cloud of boiling oil vapor, and then you let a bunch of air up the bottom of that cloud of boiling oil vapor, you're going to have a really sad microscope. So, and then the last thing, there's 3 things in the Discord, right? The last thing was, is V1A and V1B sealing properly? So if V1A or V1B isn't sealing properly, let's say you go to vent your specimen chamber. So you close V1A, you close V7, and then you let air into your specimen chamber. If air rushes past V1A, then that just gets back, again, we get air into the hot boiling oil, and you know what happens when we get air into the hot boiling oil? The hot boiling oil travels everywhere in the microscope, and sad things happen. Any questions?
No.
No? Okay. So we are going to go ahead and let's just get a baseline to start with. So go ahead and, so you see, you'll see on the board down there, there's positive and negative signs on each of the on each of the test points. So go ahead and clip. Let's start with PG3.
PG3.
Yeah. So go ahead and clip the probes onto the PG3 test points. Map Labs is nailing the explanation. Wondering what happens if you try to deep fry something in silicone oil? That's a great question. Help. What do you need help with?
So I see PG3.
Yes.
This is negative, this is positive. This would be positive.
Yeah,
right?
the red one's positive, yeah.
And I do this.
Yep.
And on which part of it?
The in between the top and the middle ring. That middle ring's there just to keep the probe from like sliding back too far.
Okay, so like this?
Yep, exactly.
Like this?
Perfect.
Okay. And then the same thing with the negative one?
Exactly.
Okay.
So decontaminating oil everywhere using a plasma cleaner is not possible on diffusion pump microscope because the plasma cleaner you have to operate at a higher pressure than the diffusion pumps can tolerate. So if you decontaminate this much oil using a plasma cleaner on a turbo pump microscope, you're probably going to leave some residue behind that you don't really want to, but you could try it. So let's figure out. Okay, so the probes are almost connected correctly.
Okay.
So it's the pair of points underneath each of the PGs.
Yeah.
So you have the positive probe connected to PG3 and the negative probe connected to PG2.
That is not how the labels look.
Because the two are next to each other, like closer to each other.
Yeah.
Yeah.
Okay, so
The positive probe is correct. It's sets of two. That's the first set, second set,
yeah,
third set.
okay,
Yeah.
they're like far. So it's this one and this
Exactly.
one. That means this is the negative.
Yep.
And this is the positive. The positive was
Exactly.
correct in the first place. Is this correct?
That is correct. So now we're reading something more like what we expect. So we'll zoom out slightly so we can see the, we just got to pan down so we can see the multimeter. Except we're getting perfect glare. Do I have the thing? I have the thing with me. I love having the thing with me. This thing's kind of cool. Look at that, chat.
I have questions.
Yes.
Those are microamps.
Yes.
That is different from either of these numbers. Well, why? Is that a rate? Like, I don't know how to read these compared to what we're seeing there.
Those numbers are microamp too.
Okay, but like, are we supposed to say, let's see something in a specific range, or like?
So we are at
color?
ultimate vacuum right now, so we
Okay.
should see 0, or
Okay.
very, very close to 0.
Okay, got it. So the 0.29
Is
microamps
is very close to 0.
Okay.
Yeah.
But like, how do you know that we're like? How do you know is? Can I tell based on that what we're supposed to see?
Based on, what do you mean based on? So the 2 on the bottom,
Yeah.
that 0 is your high vacuum setting, and atmosphere is just 250.
Okay.
So if we're at high vacuum, you should see 0. And if we're at atmosphere, you should see 250.
Okay.
And then the other ones, 220 and 120, those are ranges that tell you where things should be, or those are set points where the microscope should take certain actions.
Okay. Cool.
Okay, so let's see here. What do we want to do first? Let's get the sample exchange rod out, which I think we moved out here. You know, we'll use the test plug that was being used earlier.
Okay.
Actually, we don't even need to do that. We're going to do the most dramatic version of this test. Actually, so let's do this first. DigiRen's already done this, but we'll just go ahead and check to make sure this is still the case. Can you? I'm gonna take notes, and can you move the gauges once I'm ready to take notes? Can you move the gauges to the other two pairs of test points?
Which is PG2.
Yeah. But just let me write down this first. So what are we at?
0.29 microamps.
Okay. So what's PG2?
Second. The labeling is like really throwing me off on this. Zero point 3.5.
Okay, PG1.
4.36. It fluctuates.
That was negative.
That was negative.
Yeah.
Okay, yeah, you're right. I didn't see that. Negative 0.9. No, it's 0.0.
Okay, so that's our starting point. So let's go back to PG3. So the way we're going to test PG3, or the way we're going to test V2 to make sure air is not leaking past V2 is we're going to get it so that there's atmospheric pressure on the other side of V2. And we're going to see if V2 holds and that there's no rise in pressure. So the way we're going to do that is we're going to do manual vacuum valving mode. So we're going to put the microscope in full manual. So if we make a mistake in manual, we can send oil back into the microscope because we valved it wrong. Isn't that fun?
I trust your judgment.
Manual is great. So go ahead and set the RP switch to on.
I have to step on your foot.
Okay, set the RP switch to on.
Yeah. This one?
Yep, RP is on, good. Set the DP switch to on.
Okay.
We're going to do three-way communication for this. So I'm going to say what switch you're going to do.
Mm-hmm.
You're going to repeat it back to me.
Okay.
And then I'm going to say, and I'm going to confirm explicitly that that's the correct switch. Okay?
Yeah.
Okay, set V2 to on.
V2 to on.
Set V2 to on. Okay. Make sure all other switches are closed.
All our switches are closed.
Okay, all other switches are closed. Set the auto manual switch to manual.
Okay, it's set to auto right now. So auto manual switch to manual.
Correct, set the auto manual switch to manual. Ooh, we had an air pressure alarm when we did that. That's because of a flow rate restriction in the pneumatic system. So somebody put a flow gauge, like a flow meter, in line with the air supply going to the microscope. And it's not just a flow meter, it's a flow rate limiter. So sometimes when the microscope does things, a lot of valves all at once, not enough compressed air can get to the microscope, and it triggers the air pressure alarm. So we need to delete that, because activating all the valves should not have, so did you see the air pressure light up for a second?
Yeah.
And then it closed V2.
Yeah.
Even though we have V2 set open manually.
Yeah.
So that's suboptimal, right?
Mm-hmm.
Okay. So what we're going to do now is we're going to close V2.
Close V2.
We're going to walk through the whole procedure.
Okay.
We're going to close V2.
Mm-hmm.
Then we're going to open V6. And then we're going to open V5. And that's going to let air in through the load lock. So we're just going to be sucking a lot of air in. And we're going to do that for 10 seconds.
Mm-hmm.
And then we're going to close V5. So once you open V5, you're going to count to 10 and then close V5.
Mm-hmm.
And then what we're going to do is we're going to set the multimeter to min-max. And this is going to record if there's any pressure changes. Okay, are you ready for that?
Close V2.
Yeah, I'll walk you through it, but then
V2, open V6,
Yep.
open V5, count to 10, close V5.
exactly.
Okay.
Okay, are you ready?
Yeah.
Okay, close V2.
Close V2.
Confirm close V2. Okay. Open V6.
Open V6.
Confirm open V6. Okay. Open V5 for 10 seconds.
Open V5 for 10 seconds.
Confirm open V5 for 10 seconds.
Close V5.
Close V5. Excellent. Okay, so we did not see any pressure rise. That's great.
What does that mean?
It means we do not have a massive leak in V2.
Mm-hmm.
We could have a very small leak in V2 that's harder to detect, but we don't have a massive leak in V2. So that is very good.
Mm-hmm.
So the worst possible thing that can happen to this microscope's vacuum system is not currently happening.
Yay.
Okay. Close V6.
Close V6.
Confirm close V6. Open V2.
Open V2.
Confirm open V2. Okay, excellent. So we're back in kind of a steady state now. So our first test, which is V2 leak by test, has passed. Good stuff. Okay, so now this is where things get a little bit more interesting as far as like how we get the testing to happen. So we want to check our RP to DP changeover point. So the way we're going to do that is we're going to record it. We're going to record an actual trace for this. No, we can't do that. We don't have a transit P. We don't have the right type of oscilloscope to do that. Okay, we're just going to do that with the multimeter. Okay, so the way we're going to check this is we're going to move our gauge, or we're going to move our. What do we want to do first? Let's do the chamber first. So go ahead and move the probes to PG1, which is our chamber gauge.
Mm-hmm. What is the?
It's Pirani gauges on this microscope as well. It's in min-max mode on the multimeter, so it's telling you every time the value changes, and the value is going up so quickly that it's kind of changing a lot. So we can stop that. We don't need that. What we do want though is we're going to make a recording of this. We're going to record a trace using this. We're going to set save, record. We're going to make sure our interval is 1 second. We're going to set our duration longer. Okay, so we're going to start our recording. So now it's taking 1 sample every second. We'll be able to like look at the trace of what we do after this. Okay, so now we're going to take the microscope out of automatic vacuum mode. So manual auto switch set to auto.
Manual auto switch set to auto.
Confirm manual auto switch set to auto. So now it's pumping the electron source through V1B. Now it's pumping the chamber through V1A.
Mm-hmm.
Okay. Apply specimen chamber air.
What?
Apply spec chamber air, the vent button for spec, the yellow one. Yep.
Okay. Push that one?
Yes, push specimen chamber vent.
Okay, push specimen chamber vent.
Confirm push specimen chamber vent. Okay, so we're letting air into the microscope right now. I'm going to open up the throttle. Remember how long this took last time?
No.
This took a really long time last time. remember how many times we had to cycle this button to get the air into the chamber?
Oh, yeah.
I've sped it up some because we're going to set it to more normal parameters. We were going really slowly because we had the crystals in and we didn't know what the state of the crystals was. So this is letting air into the microscope right now. So we're going to set this to our nominal line pressure, which is 80 psi. So we're at 80 psi there. And then what's left to do is to get our throttle valve opened up a little bit more. So this should take about a minute, 45 to 55 seconds is the specification.
Mm-hmm.
And we can kind of see how fast we're going based on what our multimeter is saying, assuming the high end of the pressure range is calibrated correctly. But it's still moving very slowly. We're probably going to have to apply it a second time. Just reading the screen. Okay, cool. .236. So assuming it's accurate, it's going to need to read 250 before this thing opens up. We're actually getting pretty close here. The gap on this is opening up, so this is going to open up any second. There we go. Okay. So we are at atmosphere now. And okay, so we do have a problem with the gauge right now. So we're at atmosphere, but the gauge is only reading 237.
Mm-hmm. And it should be reading 250.
Yeah. So there's a challenge.
What does that mean?
It means that we need to do a little bit of adjustment. It means that the 250 microamp potentiometer is set incorrectly.
Okay.
Go ahead.
It is increasing slowly.
Yeah. So we're going to let this stabilize for a little bit longer, and then we're going to readjust this to be 250.
Mm-hmm.
And I will give you a tweaker tool for this. Here is the tweaker tool.
All right.
Okay, so do you know what potentiometer you're doing?
Nope.
Okay, so let's look at our diagram here. So we need to set the 250 microamp range for PG1.
Mm-hmm.
So that is that one.
Okay. So this one right here.
Correct.
Okay.
So it's supposed to only take a minute to stabilize. Feels like it's taking longer. So we're actually pretty close. It's at 239. It should be at like 250. It shouldn't. It really. I don't think it should be drifting this much still.
I bet it will get to 40.
I bet it will too. Hit the down arrow. Just to wake it back up.
Mm.
It's recording everything. It's just the screen went to sleep for power saving mode. It's going to be a theme. Seems like it's slowing down.
Yeah. I'm not sure it will make it to 250. I mean, maybe eventually.
I don't think it's going to make it to 250.
Yeah, I think it will. 241? 242?
I'm going to guess 241. Why don't you go ahead and adjust it to 249?
Okay.
Or actually, let me write down this.
Yeah, it's slowing down quite a bit.
Okay, we'll let it stabilize where it's going to stabilize.
Anything interesting in the chat?
All right, is chat saying anything interesting? Chat's asking questions about the vacuum gauge. 240.51? 52? 53? Do you want to hit the, well, go ahead and hit the screen backlight button, which is the little like sun, little light. Yeah, yeah. Cool. 0.6. It's slowing down.
Mhm.
Okay, let's call it 240.7.
Yeah. 7-1. 7-2.
Yeah, we don't want to wait forever on this. We're going to call it 7.5.
Okay.
Okay, so go ahead and adjust that adjust the potentiometer until it's reading 250.
Okay. Which direction?
You'll find out.
Okay.
It's probably to the right,
Start
but
finding things out. Is this
that is the correct potentiometer.
okay? And just turn it.
Yeah.
That's not the right direction.
Okay, so it's to the left.
That's too far. It's very sensitive,
Yeah.
but I can do it. Okay, I was very close. Okay, what are your thoughts? Should I try to get it more
Yeah.
precise? I should.
Yes.
Okay. Because it's still going up, so. Okay. I'm trying to be very careful. No. I think when I take it away, it resets it.
Yeah, it's a little bit touchy.
It's definitely sensitive to like everything. How did it get worse? Too far. Too far. Too far. I'm really bad at this.
These potentiometers are not good for this. You get a feel for them eventually.
Okay, well, I am learning apparently. Look at me just jumping around with me barely doing anything.
Yeah, that's kind of how it be.
No, it's too high. Oh my god. Okay.
If you want, if the potentiometer feels like it's like noisy or jumping around, you can kind of turn it back and forth like a few times, kind of quickly to kind of like clean it.
Oh my god.
Go ahead and it's gonna move you away from your rubber. Go ahead and like sweep it a few times.
Like turn it back and forth?
Yeah.
Okay.
I do that like 5 or 6 times. You can go relatively quickly with it too. You're just going like boop, 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 you know, just kind of like wiping it clean.
Okay, and wipe it clean.
Yeah, try it now.
Okay. We're like way off now. Look at how off we are.
Does it feel better at all, or?
Um,
If you can get it ±1, that's really good. ±2 is fine too. So that's.
oh, it didn't stay. Did you see that?
I did.
I took it away when it was
Yeah.
pretty good. And then was like, nope. No, not for you today. Like, my thought is that if it goes down after I take it away, then what if I just make it go up just a little bit higher? Can I do better than this?
It might depend on. Yeah, you can turn the backlight on too again. It might depend on what direction you're twisting it when you release it too.
Mm-hmm. Okay, how's this?
That's good.
It's increasing. You seeing this?
I do.
It's increasing faster than it was before.
It's finding its new happy place.
Well, I hope its new happy place is close to 250.
It looks like it is.
And where it's gonna overshoot. It went down by 1.
Okay, we're gonna call it 0.89. Cool. So I'm gonna hold the specimen chamber closed because you see how the specimen chamber like opened up slightly?
Yeah.
See that gap there? So that gap is like not supposed to be there really.
Mm-hmm.
That is, something is wrong. The thing that is wrong, so this is the gap I am referring to, chat. The thing that is wrong is that the wheels are adjusted incorrectly. So we're gonna have to readjust the wheels. But we will do that later. So for now, I am going to hold the specimen chamber closed, and you can release the air vent. So go ahead and release specimen chamber vent. Release the specimen chamber vent button.
Release specimen chamber vent.
Confirm release specimen chamber vent button. So I gotta hold this closed until the vacuum is low enough to keep it closed. Oh, not quite yet.
That decided to.
What? What did what?
It went up more, quite like.
Yeah, it does that right after it pumps down sometimes. Okay, so now we are going to monitor when does it close V4 and open V1A. And it should do that at 180 microamps. And if it's not doing it at 180 microamps, we have a problem.
Do we expect that to light up?
We expect V4 to close and then V1A to light up, exactly.
And we expect it at what?
180 microamps.
Okay. How are we gonna know that?
It'll be 180 microamps in the meter, and it should, and V4 should close and V1A should open. And if it does that early, if it does that at like 210, 220, then that is happening way too early, and that's letting oil into the chamber. So this is what's happening right now. You see how the line starts out? So this is the pump down trace that we're doing right now.
Yeah.
So we started out at absolute vacuum earlier. We vented it, so we went up to atmosphere, and now we're slowly going to pump down, and it's going to kind of accelerate. And then once it flips over from roughing pump to diffusion pump, it'll really accelerate. And then it'll start slowing down again. So there is no chiller in this room anymore. And so the chiller audio is non-existent because the chiller is 50 feet that way, and it's amazing. And well, okay, it's 45 feet that way. Maybe a little bit less than 45 because of some extra parts to the line. The roughing pump on this microscope is really nice. It makes a little bit more noise than it should. It should be like silent. And I can hear a little bit of a ticking sound, so that's not great, but yeah. And then the Rode microphones also help a lot on that front, but they're not really doing that much work. Like this room is actually pretty quiet, as microscope rooms should be, because like the sound shakes the microscope and it's not good.
Yeah, can confirm. It's pretty quiet.
Okay, so we are at 248, 247. It should start dropping a little bit faster here once we get like kind of the bulk of our air out of our spectrometers. $245.
long does this take?
It is going a little bit slowly.
Mm-hmm.
That is because we have the wavelength dispersive spectrometers, which are really big volumes, but it's going to speed up here.
Okay. We
it-
definitely want to pay attention at 180, right?
Yes, it should take about 5 minutes normally to go from atmosphere to high vacuum, or to being able to operate the beam. With the wavelength spectrometers on it, it does take longer because there's just so much more volume and so much more surface area. That's another reason we're taking them off or not using them, is they just slow everything down. 230. Oop. And the multimeter will record the changeover too, because it will speed up suddenly. So we'll be able to go back and look at the trace and see exactly where the rate changes. $220. I've seen microscopes valve over as high as 230, and that's a huge problem. So I'm very curious where this one's going to valve over.
But you don't think it will be at 180?
It could be. The upper and lower ends of the gauge range do drift sometimes, because the gauge can get contaminated or something, and touch the filament that's hot. That's the actual gauge filament. But the set points don't rely on the gauge filament. They're kind of their own independent thing. $296.
196.
196. Sorry.
Yeah.
Well, that's early.
How bad is that?
It's not as bad as it could be. It's not great. Okay, I don't like that. And it was worse before, because before our upper end of the gauge was 240. So it's basically 10 micrograms, approximately 10 micrograms worse than it is now. Let's see here. What are you saying, chat? Does the scope come with blinking plates for spectrometers, or you gotta hunt some down? This one did come with blinking plates, which is great. I do have all of them. Yeah, slap some foil on there. What could possibly go wrong with foil trying to hold vacuum? Okay, we got down to 7 micrograms really quickly. That's interesting, kind of a good thing. And now we're going to watch it, and we're going to see where it opens V7. And that's our HT ready set point.
How do you know that it's V7? Like, does anything in this diagram tell you this, or you just
So
know?
V7 opens when HT ready. V7 and HT ready are the same signal, kind of.
Okay. Is it the same on all microscopes? Is it like
that's background knowledge on this microscope specifically.
Okay, got it. I'm gonna bring the screen back up.
Yeah, sounds good. Oh, can I see what happened?
Yeah.
Battery's low. Oh, it's not letting you turn the backlight on because the battery's low. We'll put new batteries in a second.
Sorry.
No problem. So that's 6 microamps there. I don't mind if it takes longer than that for V7 to open. That's completely fine. Yeah, well, so you definitely do not want to make vacuum blanks for your microscope out of aluminum foil, out of aluminum plate or something, because aluminum is a lot more transparent to X-rays than steel is. So you basically, if you make the vacuum blanks for the size of your chamber out of aluminum, you're going to have a bunch of X-rays leaking out. Same thing applies for, and another challenge is, aluminum is not a magnetically conductive material. So if you put aluminum on the side of your microscope, you will let magnetic fields into your chamber. And so your microscope will be a lot less resilient to magnetic interference. So 5.2. I think it's going to happen around 3 microamps. That's where I saw it turn off earlier, or turn on earlier when we started pumping.
And you're talking about V7, right?
Yes. So we're at 4.97. We're good in there. You don't want stainless blinking plates either. Ideally, you want nickel-plated steel or nickel-plated iron. I mean, stainless steel is safe from an X-ray perspective, but it's going to be suboptimal performance for magnetic shielding. And stainless steel is a great vacuum material, so it's kind of annoying that you don't use that. If you use steel on its own, not a great vacuum material. Nickel-plated steel, great vacuum material. Oh, where did it do it? 4.27? Okay, I'm fine with that. So now we need to adjust where that changeover happens. So that's fun to do. Yes. I do have another thing that will tell us what direction to turn that one. Oh, are you okay?
Yeah, I'm good.
Okay.
Sorry.
Boop. Let's see here. Helpful documents.
So like, how do you adjust that if it's not just sitting there like the 250?
Ah, you're asking the correct questions, Maria. Good job. No, it completely sucks. It's not easy. It's kind of trial and error, and more error than trial.
So do we have to go back and forth after we adjust?
Yes,
Oh
yes
my
we do.
God. And we still want to get it within 1 microamp.
No.
This is going to take all night.
Well, I'm checking other documentation. Other documentation is reporting 210, which I don't like. This one's wrong. It's 180. But the one this does have is turning it
Maybe I decided to go with 196 and split the difference.
we're using the 180 spec. I know that that's correct and that this one's wrong.
But it's right in the middle of them.
Oh, you think somebody else did that?
Yeah, I
Okay.
mean, maybe. I don't
Yeah.
know. It is suspiciously close to being in the middle of the two.
I'm going to take a picture of where our potentiometers are right now.
Did we take notes on when we actually saw the change?
The multimeter did for us.
Okay.
I did not write it down though.
Like, I remember right now that it was 196 and like 4 point something, but we need to adjust them.
So the potentiometers actually have little arrows. Oh, you see that one that's an arrow, so you can tell like where it was set previously when you're tuning it. So I believe it's counterclockwise makes this go lower. That was your experience with the other one, right? Counterclockwise made the number go lower. Or no, well, these are different actually. So I think these ones are counterclockwise and the other ones are clockwise. So we're going to go with counterclockwise. So we're going to make a very small adjustment counterclockwise. And I am going to find my notepad. There it is.
Clockwise made it go higher.
Yeah.
On the only one I was doing.
What?
Counterclockwise made it go higher.
I think it's reversed for these ones because like this part works differently than the other one.
Okay.
Okay, so
That's just what happened on the one I was doing.
So attempt number 1, our changeover was at 196?
196, yeah.
Okay, so what we're going to do is we're going to vent it for a little bit until we get up to like 210, and then we're going to release the vent, and then we're going to have it come down, and we can just kind of like keep going up and down and testing it. Does that make sense? So go ahead and give it a little tiny move to the left this time, or counterclockwise, and then we'll test it. Sound good?
Yeah.
Okay.
It's the correct one, right?
Correct. So tiny move.
Yep. Okay, I think it was.
Cool.
But I guess we'll find out if it was enough.
Okay, so go ahead. So apply spec air.
Okay, spec.
Apply spec air.
Spec vent.
So, yeah.
Yeah, spec vent.
Yeah, correct. Apply spec vent. Release spec vent.
Release spec vent.
Correct. So now we can monitor. So some microscope manufacturers have actually put mu metal on the inside of chambers, and you can also put mu metal on the outside of chambers, but usually you use a highly magnetically permeable steel for your chambers. So we can go ahead and release spec vent faster next time.
Okay.
Just do it when you see it cross 200.
Okay. Sounds good. Are we waiting for it to go to 250 now?
No, it's pumping. Just got a little bit momentum.
Still going up?
Yeah, it kind of does this when you go up in pressure. At the high end, what we're basically doing is measuring the temperature of this filament, and so the filament can like take some time to warm up and cool down at higher pressures, more so than lower pressures.
Okay, it's going down now.
Cool. You kind of get into a pretty. You kind of figure out like what the timing feels like for a particular microscope. You kind of like how much you got to like vent it by to get it to go up high enough, and you can adjust it. And then something you can also do if you're really far off is you can turn it down, and then as your pressure starts to fall, you can turn it up so that, or then as your pressure kind of gets close to where you want it to be, you turn it up until it flips over, and then you kind of know you got it in approximately the correct spot, and then you can make small adjustments from there. Like you can kind of like have it, so as pressure's coming down, you can adjust the set point so that it comes up and meets it. So you can kind of like find it, like a coarse finding of it. Does that make sense? Nice. 237. It's falling faster this time, I think. And that's because no water vapor got into it. It's just dry nitrogen this time.
So we're waiting to see when it'll switch over, right?
Exactly.
And if it changed from 196.
Exactly. LK99 superfarad cages, yeah. We want room temperature superconductor microscope. Microscope shielding would be great. I would appreciate that a lot.
195.
Nice. So we are lower than we were.
Yeah.
Down arrow.
190. 189. We'll go too far. I went too far.
If it's within 5, it'll be fine.
I don't have that confidence. It is not.
Okay.
You want to try it
Go
next?
ahead. Go ahead. No. Oh, okay. You were only 10 low. Okay. Adjust it to the right a very small amount.
Are you sure you want me to
I
do
haven't
that?
felt any of the potentiometers today. You felt the other one a lot more than I did today, so I think you're actually better
I
equipped.
saw how jumpy it is.
I don't have a feeling for it right now. I think you're a lot better equipped than I am to do this.
I barely moved that.
So move it even barely less.
Moving
Don't
it
even-
less
don't
would
even- don't
feel
even
like not
move it, just,
moving
like,
it at all.
touch it.
Just
Touch it, yeah.
Okay. Like at what point does it matter?
You can do it right now,
I can
yeah.
do it now. Okay. Okay. Top left. God, this is so stressful. I literally can't tell if I moved it.
Okay, that's fine then. So just apply spec air until you see it past like 180 and then release it.
Okay.
So apply spec air until you see it past 180.
Okay. Apply spec air
Until?
until I see it past 180,
And then release it.
and then release it.
Okay, confirm.
Okay.
Confirm apply spec air until you see it past 180 and then release it.
Okay. Apply spec air.
Have your finger over it.
That was really fast.
Maybe next time we just apply spec air for like 2 seconds.
Yeah. I'm not taking the finger away.
Okay, chat, where do we think it's going to happen this time? How good of a job do we think Maria did at
No.
not touching it?
I barely, I
It
don't,
usually,
I might have not even moved
last
it.
time I did this, it took me like 5 or 6 tries at least to get this one set correctly. At least.
I have no confidence that I could do it in that many. They're so sensitive. If you can feel it moving, you probably moved it too much, is my experience.
That is
today.
correct. That is, yeah,
And then if you can't feel it, then you don't know if you moved it.
exactly.
Okay, it's going back down. Okay, I did do a better job reacting to it sooner this time, but I can do faster.
I think just like do it for like 2 seconds
Yeah.
and see where we fall.
So we're coming back down. We're at 237 now, in case it's hard to tell from the camera.
So what was our crossover on attempt number 2?
It was like around 170, I think. Not exactly 170, but I think something like.
Yeah, it was like 172, I think.
Yeah. We're at 215 now. Should we just, like, when we're waiting, ask chat random questions?
Absolutely. Welcome to the chat, Gene.
Okay, now I should actually be watching this, but later
Yeah.
I'm going to ask random questions.
Place your bets now, chat, where it's going to flip over.
We should have had people bet on this.
They still can. You can get your
We're-
bets in right until it flips
We're
over.
at 192 right now.
So no matter what you did, it's still better than it was when we started.
Better is questionable. 185. I have a feeling I didn't move it.
Lower is better than higher. Lower doesn't damage the system unless it's super, super low.
Did
Wow.
you see that?
What did it change over?
182.
Nailed it. Nailed it. Dead on.
All right, so my conclusion, if you feel like you didn't move the potentiometer, you did.
Nailed it, chat.
All right.
Okay, guess
2
what?
tries.
Good job.
And now I don't touch anything for the rest of the day.
Well, guess what?
Keep the state.
Guess what? Guess what?
What?
We have to do it. We have to do the same thing again to the electron gun now.
Your turn.
No, you just got good at it. I don't have the feel for it. I haven't done this all. You get. So there's a reason you start with like adjusting to like 250 first, is because that gives you that gives you the muscle memory for the feel. I don't have the muscle memory right now. You do. So this is all.
You have years of experience. I have 0 years of experience.
But you did it in 2 tries.
Beginner's
My last
luck.
one. My last one. My last one took 6.
not a
Oh, we'll
beginner
find out. We'll
anymore.
find out.
All right, chat. You should vote. Which one of us should do the next one?
Okay. So go ahead and so you can look at the multimeter now.
Yeah. 5.
So tilt the multimeter up towards us.
Yeah.
And then click stop on the right. The F4.
Oh, gotcha.
Yep.
Yeah.
And now click F3 for trend. So that's our traces.
Mhm.
So that was adjusting it earlier.
Mhm. And I was moving it around a lot.
Yeah.
Yeah. Looks about right.
And then what we can do is if we hit the up arrow, it zooms in. So that's our first pump down attempt right there. So you can see where we crossed over at So this is where we crossed over 191.
Mm-hmm.
So you can see that knee was too high. So I'm gonna take a picture of that because that's our initial. Chat has voted.
We didn't even put up a.
But
vote.
chat voted.
Chat voted.
Chat voted.
One person voted.
Well, nobody else did.
One
So.
person voted Twitch plays potentiometer. I like that version.
Should we take a microscope support call live on stream?
Yes. Do you have an incoming call? Do it. I guess let them know they're on.
Yeah, I will let them know.
I'm gonna use this moment to caffeinate myself.
Sounds good. Yeah, they didn't answer. I missed their call earlier. We'll see if we get a call. Okay, and then let's see here. I want to move the cursor over and zoom in on the other set. The UI on this thing is fun. It takes a long time to render. So that's our second attempt, right? Because that one crosses over like 170, and that should be our third attempt right there. Yep, there you go. And you can see right where it crosses over at 180. Cool. So that is our pump down curve. And then we're gonna put new batteries in the multimeter so that we don't like lose our recording in the middle of it.
Oh, do you have batteries?
Somewhere. I remember seeing batteries. I think they're in the black cabinet right there.
What do they?
Oh,
look like?
actually, I know what drawer they're in.
Okay, what do they look like?
Double Ace.
Okay. In the black cabinet.
They might be there, but I think I know where they actually are.
Okay, then it's not here.
I don't believe it is.
Okay. Well, thank you for not making me look. Are you waiting on me or?
I was taking pictures of this.
Okay, in that case, I'm gonna get hot water.
Sounds great, and I'm going to get batteries. And we'll be right back, chat, because I don't want to have the multimeter shut down in the middle of our instrumentation run. So, however, you can still hear us, most likely.
Oh yeah, good point.
Because microphones are wireless.
Yeah, I better not say anything weird.
Although we might be breaking up. The audio might be breaking up.
So be careful not to say anything weird.
Yeah. Let's see here. Batteries. I remember them being around here.
The bananas are super green.
I noticed that.
I put them out in hopes they will ripen overnight.
That would be nice. Batteries. Okay, I have secured batteries. If I could get a cup of green tea, I would be grateful.
Yeah, sure. This one?
Yeah, that was great. You'll need more water.
Did you notice that this water sounds like a soda when you open it?
I did not. That's entertaining.
Yeah, like is everything okay with the water?
Tastes fine. Okay, chat, I have retrieved batteries. I'm on my way back. How are y'all doing? Intermission. Crystal clear the whole time. Okay, RF environment here is quite good. So I forget if it's 6 or 8 I need for this multimeter. We will find out. To avoid electric shock, remove the test leads before opening the case. That's good advice. Oh, I didn't quite fully unlock it. 90 degrees. There we go, now we're unlocked. It is 6 batteries. Okay, so I got 4. And then we're gonna probably have to reset the clock on this. Although this multimeter is in a different time zone than normal, so. Okay, we have batteries. Do you want to put them on the desk out there? No, we should have in here. Error, date and time need to be reset. Okay, set time. It is, oh, it's actually pretty close. Set date, it is the 14th, yeah? Yeah, it's the 14th. Oh, let's see here, microscope support.
Blocking the view.
Okay, it's the 14th, and then the time is, we'll go ahead and set it to West Coast time. So it's 11:22, 11:23, we'll say, and 15 seconds, and it is PM. Okay, the time has been set. Okay. This multimeter has a lot going on inside of it. It's got like a whole operating system, and it actually takes time to boot. So it's a little bit power hungry, but it's very sensitive. It has data logging mode. It has a lot of other, has a really sensitive resistance range.
Features, honestly.
Yeah, it does mean it's a little bit power hungry. 8:22. Oh, well, I set it. Okay, I set it to mountain time. That's fine. We'll address that later. Let's go ahead and switch over to PG2.
All right.
Okay, so what are we reading on PG2?
We're reading on -0.22 microamps.
That's pretty close. Are you impressed at how close they got those ones now?
I am impressed.
I think the lower range is actually easier to adjust. It's kind of like less sensitive with the potentiometer. I set the pencil down. Do you see the pencil?
There.
There. Chat probably knew where the pencil was before I did. I love the Fluke 87. Fluke 87, Fluke 89, great meters. I do like having, so there's the two things I really like on this, well, three things. Data logging. Data logging is great, so I can like do the plots. The low Z mode lets you make sure that if you're like, hey, there's like 18 volts on this AC conductor in the wall. Why is there 18 volts? You're like, I think it might just be inductance. And you can go into low Z mode and find out if it's just inductance or not. And then I also like the low ohms mode, so that's a 50 ohm measuring range. And that's like it's either 5.5 or 6 digits or something like that of resistance. So it's a very sensitive resistance range. So when you're like trying to like measure ground loops or something, that extra sensitivity really comes in handy. So, okay, let's do our PG1 or PG2 adjustment. Okay, so go ahead and apply gun vent.
Okay. Applying gun vent.
Yep, apply gun vent. God damn it. Ugh. It hit the air pressure alarm again, which is like nothing we're doing wrong here. This is just.
Seems to be a theme.
It's just somebody plumbed it wrong before, and I'm dealing with the consequences of that right now. What is going on?
They expect to be higher, don't they?
Yes, by like
By a lot.
by a lot.
Just in case it's not readable, it's 0.63 microamps.
I don't think so. It might not have actually vented. Is possible. We have pressure on the regulator. Yeah, it hasn't actually vented. Oh.
What's up?
Do you remember when we were working on the spectrometer, and we needed to like? Oh, that's so sticky. Why is that so sticky? Oh God. Oh, I regret everything. I regret everything. Why is that cable sticky? There's no reason for that cable to be sticky. The gray cable that like is the solenoid, we unplugged it to make more room when we were working on the spectrometer and never plugged it back in. And when I unplugged it, I had gloves on. And I didn't realize how absolutely disgusting that cable is. Oh my God, okay.
Is it oil? Do you think it's oil?
I don't, it's stickier than oil. I'm gonna go wash my hands, chat. I'm gonna be right back. Why? Okay. We'll deal with that later. You can just like see the stickiness on it too. The other half of the cable's fine. So I don't know what its deal is. I do not believe it's thallium juice. It does not have a 4-wire resistance measuring mode. It's basically as good of a, well, I won't say that. It is very good. It's not quite as good as 4-wire. 4-wire is better. 4-wire will get you like 7.5 or 8 digits. It's nice to have though. I like it a lot. I'll be right back. Do you want to glove up and plug the cable in? It's that gray one. It's this one.
Yeah. And it goes into what?
You see the other white plug that's right there?
I see that's attached to the cable that you're planning, but like what does it plug into?
That one.
Okay.
And the lower one's the sticky one.
Okay. Yeah. Should be easy.
Yeah. Problems you don't expect to have.
plugging in the sticky cable. Yeah, that is kind of gross. Alright, it's done. I'm out of tasks to do. I will wait for Adam to get back.
Okay, I've been. You got plugged in?
I have. plugged
Okay,
it
cool.
in. I did not touch it with my bare hands. This one is yours. This one's mine. This one is caffeinated. This one's not.
Very lightly, it's just green tea.
If you leave it there for a long time, it will be not lightly caffeinated.
I don't need all of it, just a little bit of it. Good tea break, chat.
Good tea break, in fact. I'm really entertained by this like tiny bin.
The tiny
5
5-gallon bucket, and then there's a big one in the last. Yeah,
Yeah.
We'll show chat.
That's adorable.
No, the tiny bin really is adorable. This is how you know we're on the East Coast, not the West Coast right now. Is we have Menards buckets. I love Menards.
And we have regular sized ones for comparison over here.
And it'll set the aperture really high.
Aww, a cat sent us a message.
Which one's the big one, chat? Which one's the small one?
I think your hand is just massive. There's an optical illusion somewhere in there where you put your hand on, like, hold on.
Oh, yeah.
I can't line it up well. The camera's too far away from me. But you see what I'm
Yeah,
getting
you see
at.
what we're going for. That was entertaining. I enjoyed that.
We have a very important message.
We have a
in
very
chat.
important message?
Yeah.
How important?
It's from a cat.
It's from a cat,
Yeah, but not monochroma. Which,
but not monochroma.
Yeah.
Okay. Whoop. Okay, what is this? not monochroma cat doing? Aww.
So this reminds me, I take a lot of meetings from home, and cats like to crash work meetings. So like, a lot of times you'll be in like a really serious meeting with like upper management, and then a cat just like crawls into your lap, and then like I don't really know what to do. Sometimes I kind of move it out of the way, and then other times I'll let it sit. I've had it like work in my advantage before, where I had to work with a really serious, borderline, like, angry team. And I call into a meeting with them, and then there's, like, 3 guys, and they look, like, very stern. And I have to ask them to do something that they don't want to do, and we've already had discussions about it, and now I'm, like, calling a meeting. And they look like they were about to, like, tear me apart in this meeting, and I was prepared for that. I work for a team where we often like are receiving that kind of reaction, and my video comes on, and I'm holding a cat because the cat just like crawled into my lap like literally seconds before that, and they see me with my video with the cat, and then they all like melt. They start smiling, and like, and they look so happy, and they were like, we're going to help you. Aww. We're going to do everything you're asking us to do. And I'm like, oh my God, I need to use this more. I need to hold more cats.
Yeah. That's a good strategy.
Like, for context, I get so much anger from teams at work. And I was just like, the power of holding a cat.
Power of holding a cat. Math Labs, you're telling me they fixed the contrast on the 289? It's so bad. It's so bad. Oh, it's so bad. Oh. I do not like the contrast on the 289, which is what we're seeing right now. Okay, are you ready to for round 3 of vacuum gauge setting and adjustment?
Yeah.
And we have a screen now. Oh, let's
round 2 or round 3?
Well, we did round 3. It's kind of round. It's kind of round 3.
It's round 3. It's part 2, something like that. Let's do it.
Okay, the recording has started. So we can go ahead and cycle. Okay, so cycle gun vent. So press it and then, so release it and then immediately press it again.
Immediately?
Yes.
I'm not waiting for any number.
Correct. You're just going to go boop, boop.
Okay, cycle gun vent.
Confirm cycle gun vent. There we go. Okay, so now we're going to see where it lands and if that's at 250. We'll let it stabilize for a little bit. It is looking like you are going to get to have more gauge adjustment fun times.
This is my curse of the day, or learning opportunity.
Learning opportunity. Learning opportunity.
It's not broken. It has tons of opportunity.
Okay, I think you know what's going on from here. Go ahead and write down once it approximately stabilizes. Did I bring my notepad with me somewhere?
You dropped it. I think I handed it back to you, and then I don't know
Did
what
I
happened.
bring it with me to go get tea?
Did you take it to wash hands? Did you wash the notepad?
I set it down right here.
Okay.
So you can go ahead and
240. This one is like not as bad as the last one. It's still moving pretty fast. I think it's gonna get closer, which means it will be harder to adjust probably.
Okay, so you've got your atmospheric pressure start, so you're going to write down what it starts as, and then you've got atmospheric after, so you're going to write down
After it's adjusted.
yes, and then you got attempt 1, and we'll see if you get that far.
Okay.
So attempt 1 is going to be just seeing where it crosses over into the diffusion pump vacuum. So
it's still moving pretty fast, honestly.
okay, then
Like,
probably
can I
want to
give it,
wait a
like,
little bit
another
longer,
minute?
and
Yeah.
I will be back in a second. Chat. Bye.
Bye.
Replacement screens. Ooh, a new screen for my 289. I like that idea.
I am not a program manager, but that's a good guess. Because they also get a lot of anger from many teams and work with many teams. I am closer to a program manager than I used to be, but technically I'm still an engineer. Bye! I work in power and battery life. So I make sure, like, an entire company doesn't use too much power on their devices. And most people don't think about power when they do things, especially in software. So that's where the, like, I don't want to say hostile, but the contentious nature of our relationships comes from. Did pretty good here. We might actually get to 250. I'm optimistic. We're at 247.63, 64, 65. It's still moving up, so I'm gonna give it like another couple of minutes. Nope, don't dim the screen. Not sure if I want to use the backlight though because of the batteries. Vacuum system checking is almost as swift as Windows 95 from floppies. I can only imagine. Losing their power as in like permanently or like what does that mean? They're not going to be powering like people's houses anymore? Like I don't think I make people that angry. But probably close. All right, let's check on this again. We're at 248.5.
Oh, that sounds great.
We're getting like really close. Like it's slowing down now, but like no, I don't think I'm gonna get closer. Maybe I will get closer. I don't know.
What did you say? 248 point what?
248.55 right
That's
now.
plus minus 2, so I think we're good.
Yeah. Yeah. Okay. I don't have to do anything.
I need a microphone.
I feel like if I touched it, I'd make it worse. 248.6. probably call it what, like, do you want me to write it down or?
I already got it.
Okay.
248.6. Okay, cool.
248.66.
So let's go ahead and so what are we gonna do now?
We want to capture this
Yep.
number. And in order to do that, does anything happen to this?
Oh, actually, all the lights are burnt out right now. So that normally that button would be lit up, but the bulbs are all burnt out.
Okay.
So you gotta, yeah, you gotta release the. I say release it because the button's coming back out.
Yeah.
So
Yeah.
release gun air.
Release gun air.
Yep. Confirm release gun air. So this one moves a lot faster because it's a lot smaller.
What's a lot smaller?
The volume we're pumping.
Okay. Got it. And are we waiting for something to switch over at 180?
Oh.
Oh.
Well, that was early. So
That was
like
197, I think.
I think I saw 201.
Okay. Maybe you're right. It was moving really fast.
Yeah. Okay. So let's try and get that. So we need to adjust that down. So we switched over at 201. We want to switch over at 180. So let's get that better.
Okay. I think it's the top one, right? Yeah. It's the top left one again on PG2.
That's correct. Well, actually, let's go. Wait a second. Let's see where. Well, actually, V7 won't open.
You want to see when the next one is?
Yeah. Well, V7. Well, I guess V7 will open, but V7 could also be opening because of what. So, we're waiting for V7 to open for HT ready right now, but PG1 could have also gone up because of this being pumped down. But V1A is closed. If V1B is not fully ready, then V1A stays closed. So checking on if the interlock for this one's set correctly. We could flip the meters over. I don't really want to do that right now. So we're gonna see where PG1 does open, but we might have to investigate that a little bit more to make sure that's correct. Yeah, I read something about that too. I want to read more about it. That's like, did you hear about Lake Tahoe?
I did now from the
Yeah.
comments.
Okay.
I don't know if there's anything else there.
They are not rotary ball valves. They are so V1A and V1B, the high vacuum valves, are butterfly valves. V3, V5, well, V3, V4, V6, and V2 are pneumatic piston valves. V5, LV2, LV3, LV1 are solenoid valves. LV4 is also a solenoid valve. And V7 is a gate valve, basically. Okay, chat, place your bets. Where is it gonna open up V7? We're at 5.77 microamps. Let's, is it gonna happen at 5? Is it gonna happen at 4? Is it gonna be at 3? Is it gonna happen at 5.5? Is it gonna happen before the battery in this camera dies or not? I don't know. Speaking of, I'm gonna go put a battery in a charger.
It's lower than 5.5.
Well, if you guessed 5, you're wrong.
Wait, no.
Oh, it's lower than. If you guessed 5.5, you're wrong. When you move a machine to a drastically different altitude, will it throw off the settings? I don't think so. It could slightly change your atmosphere setting, but probably not by an amount that matters. And then the Piranha gauges aren't measuring the difference between atmosphere and vacuum. They're basically just measuring vacuum.
We're getting close to 5.
Well, it's below 6, so we know like it's okay.
Mm-hmm.
I'm kind of curious where it actually is, but we might end up adjusting it up some later, but it's fine for now. This one doesn't do anything that's like vacuum critical. It's high voltage safety critical because for the integrity of the high voltage system, because it makes sure that you can't turn the voltage on with the pressure too high. Monochroma is wondering what they have missed.
Oh.
We explored the noise a little bit, or explored the oil contamination a little bit. We are testing the vacuum system now, because we want to make sure the vacuum system is checked out before we Hey, this microscope's owner's popped into the chat. Hello.
Hey.
Good to see you. I promise we're treating it well. Yeah, well, okay. Monochroma is gonna have flashbacks because of that one. It's not at all like that other microscope monochroma. The metal shavings are not in a place I can attribute to anything on the stage. I don't. Okay, maybe they're from the sub-Z axis. It's possible they're from the sub-Z axis. They're not from the tilt. It's okay. They're not from the tilt. Everything's fine.
We're at 4.25.
And we still haven't crossed over? Okay.
We still haven't.
So we can definitely adjust that up a little because it doesn't need to wait this long.
Okay. Do we want to, I don't know, make any note of it, or?
Well, I have a spot to write down where it opens.
Okay.
I think I'm just going to write less than 4.
Oh, hold on. We haven't gotten to 4.
We'll get to 4, then I'll write less than 4.
Sounds good. Good plan.
So the brush, they're not on the X and Y. They're not on the Z, or the main Z. They're not on the tilt at all. The tilt's completely fine. I did check under the tilt gear. There was like nothing nearby that would like do this except maybe the sub-Z. If I had to guess, I'm thinking maybe it was like a collision with the optical microscope, or it was a WDS something like dropping shavings. Or maybe it was the like the lead flap shields on the WDS, but it wasn't. It's not from anywhere that can come from like one of the main axes. So I have not determined that. We'll look into it more. It's a pretty small pile too, relative to other things that we have seen. Okay, we're at 3.75. I'm going to call it less than 3.75, and we'll need to adjust that. Okay, so have you made any adjustments to the potentiometer yet for the 180 set point on this one?
Nope.
Okay, go ahead and do your predicted adjustment.
What was it at? You said it was
201.
around 201.
Yeah.
For this one, do you know which direction?
The same direction as the last one, because we went down to the last one too, so that was counterclockwise, right?
Counterclockwise, yeah. Okay. Is this the correct one?
Yes. So what do you think? Can you want to feel it move or not? Oh, what did it do it at? 3.43.
Yeah, 3.43.
Okay, hang on a second. We
We have a number.
no, we lost a battery in that camera. Do you want to take that camera off the tripod? It's a little button on the left side, and it comes back out towards you. And you get to unscrew that because the door can't quite open with that mounted. First time holding the M6.
Am I opening it right? Okay, yeah, I am.
Is the orientation correct for the battery tabs?
I think so. It looks the same
Okay,
as
cool.
what you handed to me. Or maybe it's this way.
I mean, you can. You had it right the first time. I just didn't know. Cool, and then there's that. I will put this on the charger.
Ah! How's that?
Looks great. Tighten it just a little bit more. Cool. You want to hit the button on the multimeter so we see what's going on?
Yeah.
I think the screen on also helps. Okay, so we're going to do a very short application of the gun air. And then we're going to... So you made your adjustment?
I have not.
Okay, so go ahead and make your adjustment.
This one and to the left and a little bit. Because last time it was off by like what, 10? And then I overshot it.
Yeah, last time I was off by 10 and you went down 20. So this time you're off by 20.
Yeah.
So theoretically, if you do the same move that you did
Oh.
the first time last time,
Yeah.
it'll be right on.
Yeah. I can't promise anything. Let's see how close I can get.
So, Matt, did you run? We found that the set point for PG1 was 10 microamps too high, which isn't that bad. Well, actually, it was 14 microamps too high. 16 microamps too high. And the set point for PG2 is 20 microamps too high, which is also not that bad. Well, actually, originally PG1 was like 30 microamps because the atmosphere set point was at 240 instead of 250. So we adjusted the atmosphere to 250, and then we adjusted the set point down a little bit, and we're doing the same thing for PG2. PG2, so PG1 is the chamber, PG2 is the source. PG2, the atmosphere set point was correct. It was at like 248.6, which is great. That's plus minus 2, which is doing real good. And we're adjusting it down a little bit. So basically both of them are off by 20 to 30 microamps. A little bit high, a little bit high. Shouldn't have been that bad, so. Okay, how do you feel?
It's definitely wrong. Sorry. I moved it too far, but I can't tell by how much. So
Okay,
I tried to readjust. So can we just see where it's at right now?
It's better to be on too low than adjust too high. Is there any chance we're adjusted too high?
No.
Okay, cool. So just like I think apply gun vent for like literally maybe not even a second. Just like on off.
Okay.
Just enough. Do it real quick this time, and then we can always do it longer the next time.
Okay. Applying gun vent.
Sounds good.
Very quickly.
Yep. So that's probably too fast because LV1 never opened.
Did again?
Yeah, like V7 never even closed.
Okay.
Yeah.
Do it again?
LV1 has to open for some amount of time.
Okay.
Good job. That seems like perfect.
It's going down. It's going to be really wrong.
So the I was basing that off of the TEM set points. The TEMs are all at 25. SEM, they actually do specify. Did we just lose the main camera? Okay, SEM they do actually specify 0 microamps instead of 25.
I overshot it by so much.
What? How low is it?
115.
Okay. That's fine.
Oh my god. 80? 73. 73. I can fix this.
You can fix this. Take it real slow on the way up, though.
Yeah.
So 0 is what we were expecting for the SM. So we didn't touch the low end at all. Okay, where did it go? Where did it cross over? Where did it cross over?
I didn't see, but it was like around 4, I think.
Around 4? Oh, okay, cool. Okay, so you want to make your adjustment?
Yeah. Yeah. Okay. I'm probably going to do less than I need to intentionally.
Yes, do that. Very good.
And so it's going to probably be incremental.
Yeah, exactly.
I'm gonna have to do it several times.
Yeah, that is definitely the correct move.
What was that?
That was V7 opening.
Oh, okay.
It seriously got down to 4 on the roughing pump? Wait, Maria, it got down to 4 using the roughing pump.
What do you mean?
It crossed over from roughing pump to V1B at 4.
Are you sure?
Is at 4.11. That's where it crossed over? That makes no sense. That should be impossible. That should be absolutely impossible.
Then what was it that happened at like 70?
Oh, it crossed over at. So wait, what happened at 70?
I thought it crossed.
When did
over.
V4 close? Or when did V3 close?
I don't know.
You see that at 70 something happened?
Yeah.
So a valve moved at 70.
Yeah.
Okay, I don't know why I wrote down 4. What happened at 4?
I thought that was this.
So 180. So 180 happened at 70.
Yeah.
Okay, that's barely possible. That makes more sense.
Yeah, because I'm pretty sure I overshot it.
Okay, so you overshot to 70, not to 4. Okay, I wrote down 4.
Yeah.
And I was like, wait a second, this makes absolutely no sense. Okay, let's do it. So you done your adjustment?
I did my adjustment. It's
Okay, go.
probably going to be less than what we need, but
That's a good thing.
Yeah. Okay.
Okay, go for it. Okay, what are you going to do?
I'm going to do gun quickly for like a second.
Confirm, do exactly that.
Okay. $155. V3 close 155 approximately.
Okay, cool.
So that's I barely moved
Like
it
25.
to get it up from 70.
Yeah, so it's pretty touchy.
It's gonna be really hard.
This is probably a you don't even want to feel it type situation.
So I was trying to see if I could do it visually. If
Yeah.
I could see visually instead of just
Visually
feeling
won't
for it.
necessarily correlate at these.
Visually is made it. I think it's made it worse. Yeah. So I need to like barely touch it.
I would try that, yeah.
Did you catch that?
So that was V1A opening, which is a little bit different. But yeah. You're good to go.
Okay. That's wild. I barely touched it and it went up from 70 to 155.
That's how it be.
That's how it be.
That's how it be.
Hear this, chat? Has anyone else had to do this? I need all the tips right now. And maybe some good
Monochroma is dealing with a different type of potentiometers problem set right now, so.
Monochroma,
I think you know what you need to do. It's just you just keep trying until you get it right.
I know, but I'm worried because like I barely touched it and it went up that much, and if I do that again, it's gonna be too high, which you said is bad.
Yeah, it's not great. But I mean, the reason we're doing this right now is because the microscope is already full of oil and we can't make it worse.
I'm sure we can make it worse.
It doesn't matter though. At this point, everything has to be cleaned, and the amount of effort between cleaning this much oil and cleaning a little bit and cleaning twice as much oil is actually the same.
Okay, fair enough. Okay, I'm gonna barely touch it and hope for the best.
Yeah, 5200 does have a much simpler vacuum system. And then the other scope you worked on has a way easier to adjust vacuum system. It's very nice how that one works. Relative to this, to a degree.
Okay.
Okay.
Let's see what that did.
Sounds good. What are you gonna do now?
Gun.
4.
On and off
Sounds great.
quickly.
Sounds great.
Let's turn this on first.
You can go a little bit faster.
I tried to do faster this time.
Yeah, but second you hear LV1 open, which is the hissing or the like sustained hissing, you can close
That's when
it.
I can close it.
Yeah.
Look, it was faster.
That was faster this time. That was really good.
Okay, let's see where we ended up.
Monochroma does say that the oil could be on fire.
$171.
171. Good job.
This one is really hard. I don't know if I can get it to 180.
You can try.
I can hold this next to it for my next adjustment. What is this called?
A tweaker.
Tweaker.
Tweaker tool.
I can hold it next to the potentiometer for my next adjustment. I can show it to the potentiometer.
That is how it feels sometimes.
Do I need to wait for the...
No.
Okay. So I can adjust
Yep.
it now.
Sure can.
Oh my god.
Are you having fun?
No. I'm really stressed.
I'm so sorry. I'm not.
You can do it.
I did fix the vent pressure. I did. It's not set precisely, but it's much better.
Okay.
Go for it.
Let's see.
What are you gonna do?
I'm gonna is it on when I push it on, or what is?
You have applied it. Yeah, you've applied it when you
Apply.
push it on. Yeah.
Okay, and then release.
Yep.
Okay, I'm gonna apply and release within
As
as soon as I hear.
soon as you see, you could also go as here, or when you see that light up, because that's the leak
Okay.
valve.
Okay, and then immediately
Yeah.
release. Okay. How was that?
I mean, the multimeter's gonna tell us. That's pretty good. Was working on a project where there was a concern that cavitation within a piston pump system was degrading the silicone oil. Oh, that sounds like fun. Sounds like a lot of fun.
172. I didn't do anything. I barely. Yeah.
That's fine. I think you should. I don't think you should take that as like you should do the same. You shouldn't do the same thing again. I think you should feel completely comfortable doing the same thing again, and just seeing what it does.
Okay.
Okay, go for it.
This one's gonna take me like 10 times.
That's fine. I've spent a lot more than 10 times doing this, especially for these small moves.
This one is harder than the other one. Like it feels
More
more
sensitive.
to me.
Yeah, sometimes individual potentiometers can be weird.
Okay.
Okay, go for it.
That I did nothing.
Go for your next step.
Okay. Gun, apply, and release.
Go for it.
As soon as LV1 comes on, right?
I think you know what you're doing now. You can just go through your cycle.
Okay. Hey, 180. I missed it, but it was around 180.
Chat, what was it?
Chat, what was
Okay,
it?
just try it again.
Okay. I'm good to go now?
Yeah.
Okay. Okay. So again, gun, apply and release.
Chest is 182. 2 people in chat say 182.
Okay. If you would like to get it closer than that, I think you should do it
Nope.
because I don't.
Plus
think
minus
I
2.
can.
It's
182.
182. Good job. 7 attempts. Well, 6 actually. Hey, you did it in 6.
Was it?
Yeah.
Cool. Yeah, I really messed up the first one.
That's you just gotta guess and check with these things. 'Cause so the potentiometers aren't necessarily linear.
Mm-hmm.
So sometimes they're like a small move on one in one particular spot might be a really big jump,
I think the problem with the first one was that I moved it,
and then you move
and
it
then I
back.
thought I moved it too far, so then I tried to move it back, and then he told me that too high is worse than too low, so then I moved it back to make sure it's definitely too low.
Making sure it's definitely too low was the correct move.
And that's how we got like super low.
But
and then I
that
had
was
to,
fine.
like,
That was
carefully
like
bring
that
it
was that is how you should do that. That was a good idea. You did good. You didn't ever exceed it. So you only made it better. Cool.
All right. Next one we do Twitch potentiometers.
How does Twitch do this though? Twitch doesn't have
I don't know. I too much responsibility.
Okay. So from here, we're going to see if we've got a V1A or V1B leak. So what we're going to do for that is we're going to hook up our probes to PG3, and we're going to monitor PG3 as we apply things. But well, actually, first what we'll do, let's check for a V7 leak first. So to check for a V7 leak, we keep our probes on PG2. We gotta let this drop a little bit longer first, and then we're gonna apply specimen chamber air, which is gonna pressurize the PG1 section. And if air is leaking past V7, we will see that as a pressurize on PG2. So we got the specimen area, right, down here, and we've got the source area up here, right? So we're gonna open LV3 via that button. That's gonna let air into the specimen area, and then we're gonna look for a pressurize on PG2. And if PG2 goes up, it means that air is leaking past V7.
Okay.
So we're on PG2 right now, which is correct, and we're gonna let this continue to drop a little bit so we can get as sensitive of a measurement as possible to see if we have a V7 leak.
What opens LV3 again?
LV3 is opened by the specimen air button, or specimen vent button.
Okay. And then we want to see if LV1 lights up.
No. If the pressure on PG2 increases.
If the pressure on PG2 increases. Monochroma says this is golf scoring.
It is golf scoring. It is absolutely golf scoring.
Right? Or like, it makes me think, what's that card game where you have to get to 21, and then but if you go over, you lose?
I don't.
As close as you can. I don't remember. But
You can tell I've not been to Vegas.
I played as a kid, like in Eastern Europe, like before being.
I played it before. I just don't remember. Which one is that? Somebody in chat will know.
Blackjack.
Blackjack.
We call it something else in Ukraine, but I don't remember.
So far the vacuum system is looking good. This is good. These are good things.
How low do you want it to go?
We just want it to start moving as fast.
Cool.
Check out what chat's saying.
Is it interesting? It's always interesting. Oh, Cousins Lviv, that's amazing. Thank you for the money for drones. My brother is in Kiev now, and some other relatives. So yeah, we definitely appreciate it. Trench candles. Wait, what does that mean?
I don't know.
What is NAFO?
I don't know if the filter will let them type whatever NAFO is.
Okay. Might have to do some research on my own.
I think we'll just go until V7 opens and then we'll do the test.
Okay. Sounds good to me. I'm gonna drink some of my non-caffeinated
Sounds
tea
good.
because I
North American Fishery
need that
Association.
after that stressful experience.
So just to start talking through what we're going to do once we've done finished testing the valves, we're going to pull the optical microscope off the right side of the chamber. We're going to pull the wavelength dispersive spectrometers off the chamber. And then we're going to pull the probe current detector off the left side. We're going to pull the objective aperture off the right. We're going to pull V7 off the right. We're going to disconnect the crossover, the electron source crossover pipe. We're going to probably remove the entire, we're going to remove the entire standpipe. We're going to remove the electron source. We're going to, we're going to never remove the liner tube. Then we're going to remove the electron source. Then we're going to remove the condenser pull piece. Then we're going to remove the condenser lens. Then we're going to remove the intermediate section. Then we're going to remove the upper scan coils. Then we're going to remove the V7 section. Then we're going to remove the lower scan coils. Then we're going to remove the objective pipe. Then we're going to remove the objective lens. So it's going to be all coming off. It's going to be great.
All tonight?
The unbolting and taking off goes really fast. It's just, we're just putting it on the table. We're not cleaning anything tonight. We're just putting the parts on the table.
Okay.
Okay, so V7 just opened. So we can do our V7 leak test now. So to do the V7 leak test, apply specimen air and monitor for a increase in the microamps.
Okay. What exactly am I watching for in the increase?
The number to go up instead of down.
Okay. Just after I apply. Apply it once. Apply specimen
Yeah,
air
apply,
once.
and then just let it go.
Okay. Applying specimen air. I don't see it going down.
I don't either. Cool. Okay, go ahead and release it.
Releasing specimen air.
Nice. So that held. That's great.
Awesome.
So now we can move our probes to PG3.
Okay.
Oh, actually, before we do that, let's stop this.
Mm-hmm.
And let's capture a picture of our trend. This is basically a report card when you record trends like this or traces like this, because if you mess something up, the trace will show. Only a few minutes. It's going to be more than a few minutes, but it's not going to be too bad. So there's what all of our pump downs look like. So if you hit the up arrow, that zooms in, and then it has to replot. And you have to wait for it to plot before you can do anything. Yeah, this is the 289 is like kind of slow at some stuff, but like I'm glad it has it. So we're zooming in on that part. Okay, so that's far enough zoomed in now that we can try one more. We can try one more zoom. Yeah, that's a good pump down curve. So that was our initial pump down curve. Yeah, removal is pretty fast. Putting things back together is less fast. Okay, so now we get to spend a bunch of time navigating to our rest of our pump down curve. So that's our initial. So we have to zoom out, and then we have to wait every time. Well, I guess we can zoom out without waiting, so that's good. Attention, please wait. Favorite notification on this.
It's like giving you a warning.
You can see as you got more used to doing the adjustment, like the frequency between the pump downs gets faster.
Yeah.
So I gotta move the cursor over. We'll go right to the center of all of them, and then we do up arrow to zoom in. Yeah, going back together, inspect, clean, inspect, clean, inspect, clean. Spent a lot of time cataloging every screw and piece so that I would know how it went back together. It actually assembled faster than it came apart. Okay. Well, in this one, there's a bunch of the wrong screws used currently, so we're just gonna take it out, and then we're gonna put back the correct screws in the correct spot instead of what it is right now. So let's go ahead and move to PG3 now.
Okay.
A couple dozen might be pushing it, but yeah, 64 is a lot. 64 is an 840, same thing. For this exact one.
PG3 now.
Okay, so you can see the pressure on PG3 spike when it opened up V1A, but it should get that back down pretty low pretty fast. So basically, we're gonna wait for that to get, that should get to 0 relatively quickly. So this is basically gonna be our last vent. And then we are vented, and then we can proceed with everything else. I'm going to slow the vent down just a little bit just to see if that's get the right adjustment for the chamber. What was our starting pressure for this one? Our starting pressure was 0.29.
It's 0.94 now.
Okay, this is it's going down real slow, I think.
Yeah.
So I think we're good to do our test.
Okay.
So yeah, so we'll go ahead and get the screen LED back on.
Mm-hmm. Nope.
LED. or the backlight. Yeah. Cool. So go ahead and apply specimen air.
Okay. Applying specimen air. And we want that to go to.
Just let it go. Yeah. So it actually started falling faster because with V1A closed, there was no gas lift from the specimen chamber. Does that make sense?
No.
What?
No.
Okay, so it closed, so we applied specimen air, it closed V1A,
Mm-hmm.
and then PG3 started falling faster because it wasn't pumping the specimen chamber anymore. There's no gas lift from that
Mm-hmm.
because V1A was closed. So we're going to let that vent fully. Yeah, you basically just pour the amount it says in it. Yeah, pump is fully removed. There are some diffusion pumps that have like fill and drain ports on the side of them. That's not these ones. Edwards makes ones that are like that. The Edwards pumps aren't necessarily great for electron microscopes, according to Joel, because they vibrate a little bit too much. We do not pour diffusion pump oil into the hole in the yard, but you know. Okay, let's see what our chamber is doing. Okay, it's just starting to split open. Cool, that split open in a pretty reasonable amount of time. That should shut off in a second. So yeah, we can definitely stuff that down a little bit more so that it vents in less time next time. Well, next time it vents, it's also going to not have the WDSs attached anymore, so. But Popular Mechanic told me to. Well, I'm not telling you to. Popular Mechanic might, but. So we're just going to wait for LV3 to close, and then we can apply gun vent.
Okay. What is that going to do?
It's going to vent the gun. Close V1B. It's going to close V1B. It's going to open LV1. Yeah, that one's going to open. V1B is going to close. V1B is going to close first. If V1B doesn't close before LV1 opens, that's bad things happen. Okay, cool. So we are at 0.67 on PG3 now, and we want to see if when we open LV1, the air leaks past V1B and makes it to PG3.
Okay.
So go ahead and apply gun vent.
Okay, and leave it.
And leave it. Apply gun vent and leave it.
And that's going to... Applying gun vent?
Yep. 0.65.
So we're going to see if it will go up.
0.64. It's not going up. I haven't seen it go up yet.
Yeah. Same.
Cool. Well, the microscope is at air now. Well, it came from the ground, back in it goes. Unfortunately, there's like water tables between the top of the ground and where the oil is usually, so. Okay, cool, still dropping. So we don't have a V1B or V1A leak. That's great. So, one more thing. What do you think about, what do you think we're doing next?
Adjusting potentiometers.
We're turning the microscope off.
Okay.
Do you like that more than adjusting potentiometers?
Yes.
Yeah? Are you ready to be done adjusting potentiometers tonight?
Yeah.
Yeah? Okay. We do still need to check on the PIG3 adjustment, but we're not going to do that.
Like, how do we, or yeah, I guess, how do we know that these are?
So PG3 we need to do with the diffusion pumps cold to check the atmosphere. Okay. And so that the microscope needs to cool down for quite a while to do that, and we're not going to wait, so we're just going to shut the microscope down and do the diffusion pump stuff later.
Cool.
Cool. So, would you like to do the honors? Turning the microscope off?
Sure, is there, okay, first of all, do I need to do anything with
Nope.
that? No.
We do not, we're not going to undo those until we have this thing back together again.
Okay. Do I need to do anything besides
Nope, you just
the
turn
key?
it off.
Just the key?
Just the key.
And it's good to go now.
Once I have the camera focused, yes.
Okay.
The camera is focused. Do it.
Okay.
Wait.
I'm not working with you anymore. Bye.
I waited until we were just turning it off and there was nothing that... Did chat enjoy that? I'm
did
sorry.
Not.
I'm
I did
sorry.
Not. I'm not sleeping tonight.
I'm sorry. If you don't get one wait in, are you even trying?
I don't have enough chamomile tea for this.
I won't do high voltage jump scares. I won't do jump scares when the microscope's on. That is, I draw a line there. But when the microscope's off, so part of chat approves.
Okay, what else are we doing tonight?
We're taking stuff off. So let's roll our table in here and start taking stuff off. This might be a good time to go make some hot chocolate before we glove up and start wrenching on stuff.
Yeah, I would appreciate a break and
Okay. I think we need to get HR involved. Plastic eating cartoon. Yeah, bacteria cartoon that floats around. Well, I'll tell you what, chat. I'm going to open up the chamber for y'all. Come on. Is the stage tilted? No. I guess the stage is a little bit high, but that shouldn't prevent it from opening. Okay. You know what? Screw this thing. I hate this thing. It's coming off now. Okay, we'll deal with that later. This whole terrible motor system can come off now. So happy this isn't attached anymore. Do not like this one. I love simplifying a microscope. Okay, now let's open the chamber. Ta-da! And then... Oh, I know what the brass shavings are from. The brass shavings are from the... I know exactly what the brass shavings are from. They're from the sample exchange rod screwing into the sample holder. You see where the threads are right here? The brush shavings are right beneath that. Okay, those are completely fine. Those are not from the stage.
They're much better than turbo pump.
Yes, much better than a lot of things. I'm gonna get the sample out of there, and then we will go. Do you wanna go make a hot drink?
I'm probably gonna take a break of it.
Okay. Yeah, you can take a break. I'm just gonna get some stuff ready.
Paplab asked if biodynamics insurance covers heart attacks and aneurysms. I feel like Nanograph should cover that one.
Should also cover that one. Yeah. I'm sorry.
The instigator. All right, I'm gonna take the microphone off so that everybody doesn't listen to me making tea.
I'm going to take a sample out of the chamber. So there's a little bit of brass shavings right here, and there's like not really anything on the stage. Yeah, staying out of the jump scare game is a good idea. I probably should do the same. So yeah, there's not really anything here on the stage that would explain that, but there is just the sample exchange. So I can show you how the sample exchange rod goes in. Oh, the stage is too far away right now. Oh, well, I also removed the stage knob that's necessary to move the stage in the other direction, but I think we can still make it work. Boop. And then that threads in like that, and that's how you take the stage out. So that's what I'm going to, the brush shavings are all right beneath where that happens. So I'm going to assume that is the source of those shavings. Okay. So, next thing I want to do is lower the pneumatic platform that the whole microscope is riding on, because I don't want it moving around unnecessarily while we are wrenching on it. So let's see here. Best way of doing that's going to be to make it think it's too high, it'll go down. Actually, we need to stop supplying it air first. So we'll cut the air supply to the microscope. Okay, air supply is cut. And this will just like lower on its own eventually. Yeah, the other way you do this is you just gently take out one of these. These things have got leaks, so it would leak down to 0 eventually. depending on the state of our other valves, the other ones may or may not leak down as a result of what we just did. So that's fully reconnected, which it is. Good. Love that. So actually, if we just disconnect one of them, then because they'll try to open, because they're trying to open to fill them more, it'll actually basically drain it out. Okay, so we got two of them completely landed. We're just waiting on this third one back here to land, and then we got our platform has been lowered. We could bolt the stage down. I don't really think that, or the we could bolt the vibration isolation platform down. I don't think that's really necessary on this one. So it's the pneumatic table though, because we're likely to be getting up or putting our feet around it and all that. I want to get that one taken care of now. I think the gauge on this one's broken. Looks pretty smashed up. Could be wrong. Let's find out if I'm wrong. No, okay, gauge wasn't in that bad. Oh, no, the gauge is definitely broken. Okay, well, we got our pneumatic platform completely vented. That's great. Let's get our optical microscope unplugged. Ventilated. Am I gloving up right now to handle vacuum components? No, I'm gloving up right now to handle cables because the cables in this microscope are kind of gross. But it's just how it be sometimes. And then I'm also going to, because we don't need microscope power for anything anymore, I'm just going to turn the main breaker off, and we're also going to unplug the microscope. So it is completely isolated from power. So this is the optical chamber microscope. This lets you, it's a coaxial optical microscope, so it's the electron beam that goes through the center of where it's looking. It is pretty cool. We're just not going to be using it, and it adds kind of a fair bit of complexity. And oh, is it already fully unplugged? It's already fully unplugged. Awesome. Love that for us. Oh, you know, I bet I know why your backscatter wasn't working. Well, maybe, I don't know. Okay, never mind. 'Cause I was gonna say, the optical microscope is blocking it, but not really. This isn't really the right backscatter amplifier. This is like a really old one. I don't know what's going on with this whole thing, so we'll take a look at what's going on with that later. But we don't have any of the optical microscope stuff plugged into it, so that's fine. Yeah, but that's an old amplifier. We'll figure out what's going on with that later. Let's see here. We've got the spectrometer cables are all unplugged and coiled up, ready to go. I guess we just need some foil and tape to cover the blinking ports. There's a lot of dust on that, so I'm actually going to go ahead and dust that some so that we're not dealing with that in the chamber. Yeah, I don't want to oil my hands either, but I'm not actually touching inside the chamber yet. I'm just touching cables. So just doing a little bit of distilled water on our microfiber here to help trap the dust. Could also use ethanol. Either would be fine. The rest of the optical microscope is pretty dusty. We'll do just a quick pass on it, but it's coming away from the microscope, so it doesn't really need to be great. The area right where it meets the microscope is pretty clean, so that's what I care more about. See here, make sure it's fully retracted. And then I'll go ahead and show you all how it moves in and out before we detach it, just because it is kind of cool. So it's also got a backscatter detector built in underneath it. So even when you fully insert it, and I'm going to make sure we're not going to like, collide with anything as I insert it. Yeah, we're clear. Cool. So even when you have it fully inserted, you still got a backscatter detector to work with. And that's the reason it's got that is you use it a lot during wavelength dispersive spectrometry, and a frequent signal you want to collect at the same time that you're doing WDS is backscatter. So it's got that backscatter on the bottom of it still. The other reason it has it is when it's inserted, it fully blocks the backscatter detector that's on the pull piece. So vacuum cleaner to clean the vacuum container. Yep, you do that sometimes. So yeah, that's the optical chamber microscope. Cool accessory, useful for wavelength dispersive spectroscopy. Also useful for electron beam lithography for mask alignment. Both very fun applications. Cool. Well then, let's I'm gonna go make a cup of hot chocolate and I'll be right back and we will get that pulled off. Okay, be back in a sec. They got a nice Keurig here, so this is a very fast process. If it's not the same BSD that it uses on the pull piece, it's very similar. To answer your question, Monochroma. Hi, I have a microphone on still. How is your Apple?
That's good.
Good Apple? Is it as good as apples in Washington and Oregon, or? Are the apples from Washington or Washington? Oh, do that. Instructions a machine tells me. Come on. I put a pot in. Let me. There we go. There's the blinky light. The blinky light of permission. I wonder what chat's doing while we're not there to monitor them. They could do anything right now. The admins are our way. Ah, yes, all the good Keurig sounds. We love the good Keurig sounds. Okay, so optical microscope off, wavelength dispersion spectrometers off, and start at the source and move down. We're probably not going to pull the standpipe off tonight because there's going to be inadequate time for, well, I mean, eventually the diffusion pump will be cold, but we'll still probably not pull the standpipe off tonight. We'll probably just focus on spectrometers, microscope, and the column. So we can't pull the standpipe off immediately because the standpipe is connected to the diffusion pump and there's no valve in between. So because there's no valve in between, when we take the standpipe off, we're letting air into the standpipe. And we do not want to let air into the diffusion pump while the diffusion pump is hot. That is bad for the pump. Bad for the pump oil. Good hot chocolate. How are the apples?
Almost gone.
Almost gone?
There's two more in the fridge.
There's two more in the fridge? Okay, cool. I will have some Cheez-Its. I still wonder what chat's doing. They be doing all kinds of loud things when we're not looking.
Sometimes while we're working and not looking, there are wild things going on.
Mm-hmm. Very true. So the best part about taking the column apart is we have to unplug the column cables. And these are the dirty column cables.
gloves?
Do it all with gloves, yes. Very much do it all with gloves territory. Well, the 4 Cheez-Its that were left in this were inadequate, so I'll be right back. I'm gonna grab an additional bag of Cheez-Its and then we will get to it. Sound good, chat? Oh, and this is where I'm actually really curious if the microphone range holds up or not. In addition to the Cheez-Its. Okay, we are back in the vicinity of the microscope. Are you ready? You feel ready? Cool.
Yeah. This is gonna go quick, right?
Mm-hmm.
Okay.
And if it's not, we'll finish it tomorrow.
Sounds good to me. I'll give chat a fair warning that it's probably quick.
Are you ready, chat?
Alright, we're back.
We're so back.
We're so back. So my intention is to go to bed by 2 a.m. tonight.
So that's gives us just under an hour.
Yeah, so my plan is at 2 a.m. I drop whatever I'm holding and leave. So if y'all see me do it, that's what's happening.
Would you like to bring the table in?
Yeah, I would love to bring the table in.
Spirit says hold the aperture or objective lens.
Make sure to give me all the fragile things closer to 2 a.m.
Absolutely.
Danger is the spice of life.
Okay, so we probably want to move these panels. So the table's going to go here.
Table is going to go where the panels are.
I'm kind of thinking that. I don't know. What do you think?
Yeah, I think that's fine. Like,
Do you have a better idea? Or?
Not really.
So that last one there is the one we really don't want to scratch because that's the front panel.
Okay, let me move this out of the way. It gets cold here at night.
The HVAC does weird things here. It's warmer in this room.
You're about to run into the...
See here, can chat. Here, we'll move this camera a little bit. That way chat can...
See the table?
Yeah.
This, maybe I'll just like wrap it around here so it's not on the table. I don't know where it's supposed to. Is this meant for this cable? I don't know. Who knows?
I think it's for the power strip right there, yeah.
There we go.
Okay, let's get our tools all out. So the only tool we need to clean up a little bit beforehand is going to be,
Oh, I need gloves.
yeah, it's going to be that one. We're just going to clean the threads on that a little bit. Oh, that one's kind of dirty. I'll have you start on that tool. Those are TEM tools, I think. Okay, so do you see the grime in the threads on this one?
Yeah.
We need to get that cleaned out.
Okay.
So you can do that with ethanol, and I will start uncabling the column.
Cool. Where are our ethanol bottles? Is this one? Is
That's
that
DI
one?
water.
Okay, this is not ethanol.
This one's the one you can use.
Okay. Cool. And clean it with microfiber and put.
We're gonna do the other ones, the square ones.
The little white ones.
Yeah.
Saw them today. They were on this table. So yeah.
Cool. And then I'll also get you a zip tie with the tip of it cut off. That way you can, or with kind of with an angle cut into the tip, and I find that to be quite effective at kind of getting down into the grooves. They tried to do a drop table. Chat. Okay, there's a groove cleaning tool.
Hold on. Okay. Oh, that's.
I got the EM grade ethanol, so not the denatured. And this is being used on a part before it's cleaned, so it's yeah, a little bit of flexibility here. Okay, so basically this whole bundle of cables is coming out. So we'll make sure everything's labeled as we disconnect it. Okay, let's see here. A5 and A5. Okay, that's good. We can disconnect that. Okay, let's see here. A6 and A6, we can disconnect that. See here, no A8's gonna have to come out.
I forgot with the foil, do you prefer the shiny or the non-shiny
What?
side?
The side that's on the inside of the roll.
So that's the shiny side.
Yeah, then that.
Okay. And like use the white cloths for everything.
You just gotta clean the threads on that one tool, but yeah, you can start with that.
Yeah,
that
I
zip
mean,
tie.
like what? Like I also need to clean the foil.
No, that's clean foil.
Okay, we're considering it clean.
It is clean.
Okay. Okay. When we cleaned at your shop,
I do not have that foil yet, but I have that foil now.
Okay, so this, oh, I see, it's ultra clean foil.
Yes.
Okay, so this one doesn't have to be cleaned. Gotcha.
If we were doing ultra high vacuum work, we'd be doing it, but this is just high vacuum work, so that is more than clean enough for high vacuum work.
Okay.
Okay, so the cables that are going down at the bottom here, these are the ones that go to the scan coils. So we'll get the scan coils unplugged. Cool, scan coils are unplugged. Let's get and all of our lenses unplugged. So that's going to be these ones up here. And I think the alignment coils, yeah, the alignment coils are there too, so that was the alignment coils. And then one of these is condenser, and one of these is objective. I don't remember which one's which. But they are labeled, so that's good. And they're not labeled condenser and objective, but they are labeled where they go. And then the last one should be the alignment, the source alignment coils. So that was that. So that, we should basically be good to pull the bundle out now. So the zip ties are in good spots on these bundles because the zip ties are where you need them or where you want them to be for removing, except for this one little loop right here, which I think we can just leave on, and it should have no problem making it through. JA14. What is JA14? I don't remember what JA14 is. Okay, and then JB6A10. Okay, so I think that's all of our cables unplugged. Yep, cool. Now I can bring that bundle up through here. Oh, we're gonna have to cut some zip ties off because there's some zip ties on that will not fit through this bundle, but just the looped ones. I think that's just 3 I saw that were looped. Kind of straighten this bundle out so that it all pulls through nicely. Okay, cool. So now I can get that pulled through, or start pulling it through. See what ends up coming out. Easily, that is. And we gotta get these up and through. Okay, all of our lens cables have been freed. Wiggle, wiggle, wiggle. Yeah, for what we're doing, cleaning this part for, that's yeah, and just the only part that touches the vacuum is just the threads at the tip.
Okay, so like this is not important?
Not at all.
That is important. Okay. Good to know.
Okay, let's do the optical microscope now.
I'm definitely like a bit behind on the chat because I'm reading these comments and like I have no idea what these are about.
These are about the ethanol that we were talking about earlier, but we got what we need for that.
Okay. That's good.
Okay, so we're gonna want to go kind of down then out with this one. Let's see here, do we have all 4 bolts in on it? We do. Oh, I got the wrong Allen key. I need pink for this, not yellow.
Those do look very similar. There's like a spot here that's really stubborn, not really coming out with anything.
And then we really only need the first little bit of the threads clean because it doesn't engage very much.
It is on the first little bit.
Darn it.
Yeah, like it's in the first half.
Okay, noted.
Like I'm not convinced that it's dirt, and maybe it's some other discoloration or something. Like right here.
Yeah, try what you can, but if it's still there, that's fine because I don't think we actually screw it in that far.
Okay. Well, it definitely doesn't come off.
And then actually, that part's out of vacuum, isn't it? It might actually be out of vacuum.
So
Can I get your help with this part?
Yep. Like you want me over there?
Yes, please.
Okay. I'm quite ready to call this clean.
Yeah,
so.
but you can come back to that. Yeah, go ahead and just set that down for now.
Yeah, I'm about to. Just getting a cloth.
Cool. Okay, so I need you to take out this screw followed by that screw.
With this?
Yes, with that.
This one first, right?
Yep. You can do the go long.
Yeah,
Yeah.
I think I need this one.
You can break it free first. I think you actually got it broken free though. Here, I can feel it real quick.
Yeah, it's free.
Cool.
I think it's like ready to come out actually.
Yeah, it's probably gonna come out. So then, if you put that end in,
Mm-hmm.
and then kind of pull back at and then tilt it back towards you, and then kind of use that to pull it out. Now it's at an angle. Yeah, exactly. Cool, and then put that in the tray. Okay, let's get our last one out.
Park spectrometers. Park.
Cool.
Did that
Yep.
do it? Is that as far as it goes? I don't think it's
Yep.
coming out anymore.
Yep. Okay, I'm gonna pull this out now.
Okay. I'm gonna take the screw out.
Not yet.
Okay.
Okay, there you go. And that screw will not be being put back in because the plate that goes in the place of this thing does not use that screw.
Okay.
Okay, Now it's time for the wavelength dispersive spectrometers, at least 2 of them, so we can get better access to the column. Or you know what? We can just do the column because we got plenty of good access from the front here. So, okay, so we'll get our column open. I need to take our gun cap completely off. So we'll do pink right here. Just gonna reposition that ground strap so it's in a more convenient location. Oh, it's actually one size smaller than pink. Can you get the next size down from pink, which I think is the green?
Yep. Can't tell because several of them are out.
Well, yeah, it's the next biggest one.
Yeah, that's what I mean. I can't tell because.
Okay, so we're taking the hinge off here. Maria, can you unplug the keyboard and take the keyboard and put it on the desk?
This one
Yeah,
on the desk.
just like on the desk behind us. Okay, and then can you get a piece of foil? Okay, so that is the high voltage. That's the electron source right there. And then Maria, you can cover this with a clean piece of foil.
Something fell off of here.
That tray's fine, yeah.
Yeah, that tray's fine.
Yeah. Just a piece of foil over that, please.
A clean piece of foil.
Yes, please.
Okay, I'm gonna change my gloves.
Okay, so next thing we're doing is the anode. So we got our anode puller tool, and then we're going to want our Phillips screwdriver to go with that.
Clean piece of foil over like the tip of this.
Yep.
And what about the ring under it?
Just like kind of over that whole thing.
Over the whole thing.
Yeah. So that's the electron source right there.
But not cleaning the foil, right? Because it's
Nope.
already clean.
It's already clean. Isn't that convenient?
It's very convenient after cleaning them all by hand.
So this is the anode puller tool. So this is a nice version of it. There's a couple of versions of it. I like this one quite a bit. So this version of it is it kind of goes around half of it, and then it's got these plastic set screws that go in. And those plastic set screws kind of hold onto it for you so it doesn't go flying as soon as you pull it out. Very nice feature. I think we'll have to put this up on the microscope to get the shot we want, to show you all what's going on inside here, which I definitely do want to show you all what's going on inside here. Oh yeah, there we go. Cool.
Oh no. There's a hole. Made a hole in the foil.
Well, it's not like we don't have a ton of that.
I'm gonna actually use this.
That's a joke. We have so much foil.
I don't need this piece because I touched this side of it.
Okay, watch out for this HDMI cable over here. Because if we yank on this, it's going to pull the camera all the way off the column. So that goes around the anode. Maybe put those 2 screws on it.
That second attempt.
And just pull up on it. There we go. Got our anode out. So this is, you want to check this out?
Mm-hmm.
You can get up on that black piece. So this is our column liner tool. Do you want to zoom that camera out? Just the big ring with the numbers.
Yeah, I just can't tell.
Just-
You can't see.
Oh, yeah, yeah.
There we go.
So here's what it looks like putting the column liner tool on. That's perfect.
Okay.
We'll pop back up here. So with that on, so I've threaded this on.
Mm-hmm.
Now we just pull it straight out. So that's our column liner.
Mm-hmm.
So there's an aperture, or there's kind of aperture on the top, there's like kind of a fixed aperture on the bottom too.
Mm-hmm.
So you can see just how like deep down the column that went. So now that that's disconnected, we're good to pull the electron source off, the emission chamber off. Yeah, we're not going to get to unipole tonight. So then we've got things on either side of our column liner so it can't roll. Okay, so now we can, so this, Maria, is the crossover pipe. This part right here, does that focus? So this is the crossover pipe. So we pull this back. Oh, we got one bolt to undo right there. Can you get the yellow Allen key? Maybe it's orange. Am I holding it? Okay, it's orange. I actually got it already.
Oh, nice.
Okay.
Bionomics says, Adam, rate my cleaning job on liner and anode.
I will evaluate that shortly. The anode looked good. So you see how this crossover pipe slides back?
Yeah.
So there's an O-ring in here that this slid on.
Mm-hmm.
So now you can take pink, I think, pink or green, and you can disconnect these four bolts there. So you see these four?
Sorry, can you point them to them again? Yeah. Okay.
Yeah.
It is pink. unscrew, like not unscrew, but like loosen all of them?
I'll unscrew them completely.
Unscrew them completely. It's not,
Yep.
it's not gonna like slide off.
It's not going to slide off.
Where do you want me to put them?
You can just put them in a pile where it's convenient because we're going to be threading them back in to where they came out of once we get the part off. Okay, mounted the tripod in a slightly more rigid spot.
How bad is it to drop something down there right now?
Because it's already all coming apart, it's not the worst, but it wouldn't be great.
Okay, I'm just gonna put them like in this other corner of this
Okay,
tray.
sounds good. Okay, I got this camera really wedged in there now. Okay, do that one next.
Okay.
Okay, I got it. So start on this one now.
I can't reach that.
Okay, can you hold the chamber? Just don't put your glove on the inside there.
Okay. Holding the outside.
Okay, I'll trade you. And then you're just going to put them all back right where they came from.
Okay.
There we go. So that is our emission chamber. And then on the bottom of it is our source alignment coils. So that is the upper and lower source alignment coils. Okay, so go ahead and thread those 4 back in. Okay, that gunk you're working on is high enough up to that, doesn't matter. So I'm just going to put this in. So this is our condenser pull piece removal tool. And yeah, that part of the condenser is actually not even at vacuum, so it doesn't like matter for, I mean, it matters a little bit, but not as much as other parts of the microscope for cleanliness. And then we'll get our condenser cable free. Okay, condenser cable is free. Having fun?
have mixed feelings. Mostly fun.
What is the mixed feelings?
70% fun, 30% want to go to bed soon.
Well, that's what's happening because this is going pretty fast.
Then having fun.
Okay, you can loosen these 4 bolts here by 1/2 turn.
Okay.
Actually, we're gonna pull off the objective aperture first. So that's the objective aperture right there. Rick, can you zoom this camera in on the objective aperture?
This one?
Yes, please.
How do I tilt it down?
Knob on the left side.
This one?
Yeah. Loosen it. Push the knob forwards. Yeah,
Yeah.
now use the handle. Cool.
There we go. Yeah, perfect.
Go ahead and zoom in on this. Yeah. There we go, cool. So that is our objective aperture. Filthy. All 4 apertures are filthy.
What's on it?
Just black stuff, but I don't see a ton of oil on it. So this has been cleaned. Oh, there's some like grease back there, but that's not bad. So this has been cleaned like somewhat recently-ish. Okay, so let's do the PCD now. So the PCD is a flat-headed screwdriver. So disconnect the cable on that. Disconnect the air line on that. Can you put the this flathead in it?
Is this the one that you push in? No. Is it?
Push out that part.
Push out.
Lift that ring up.
Lift this up. Where's this go? Is this one of these?
You can leave that one out because we're going to use it in like 2 seconds.
Okay.
Cool. So then go ahead and you see the flatheads right here?
Yeah.
Yeah. Let's start on the far one of those. I just got to find the right pair of pliers we need. There we go.
Like the 2 big ones, right?
Yeah, let me get this airline off first. That'll just be easier. Huh, did somebody cross thread this? This is really hard to take off. Usually this is not that hard to take off. Something weird's going on there. Figure that out. Okay, so yep, those 2 big flat ones.
How far?
All the way out, please. That's out. Okay, that's out. Go ahead and do that one. Good job.
Sorry, this one's
Yeah, no, it gets weird.
a little harder, like the angle.
Yep.
It's worse.
You're really close.
I think it's out.
I think it's out too, yep. So you can pull that out. So that is our probe current detector. And the probe current detector is electrically sensitive, so it has this insulating mount, and this other part's also part of the insulation system. So this whole thing is like electrically isolated and grounded only through its coax cable. Okay, so you can switch back to the Phillips bit now, and you can remove these 4 brass screws. And I'm going to go turn a water chiller off because we're getting to that point pretty soon. You see the 4? It's these 4 brass screws. Can I just see the bit real quick? I just want to make sure it's the right bit for that. Sure is.
Okay. What about the piece that's attached?
Yeah, it's going to come off too.
Okay, put them where? Like in a tray or something?
They're going to go right back where they came from.
Okay.
Joel was on their shit with these. Okay, so we're going to disconnect one of the objective water lines. And we're marking, I'm going to mark them with 2 different color zip ties. We're going to do the same for the air lines. Okay, you got those 4 out?
Yeah.
Okay, so go ahead and remove the, so this is a part you need to pull straight up on.
Mm-hmm.
And you want to minimize the amount it's like moving around or, or hitting anything. So kind of get both hands in and
Okay.
pull straight up on it.
But just this part, right?
Yeah. Cool. So this is magnetic, so this is very sensitive to impact.
What can I not touch?
The area you're touching is good, and then once you get it out, you want to handle it by that ring where the screws were.
Okay.
There you go, cool. So that is the condenser lens pull piece. So that is like that is the optic that forms the beam.
Where does it go?
It's going to go on the table. We're going to want to make a kind of a nice home for it so that it doesn't roll.
On the table, like where the on the foil, or?
Yeah, on the foil.
So like here.
Yep. Okay. And just set it down very gently. Most excellent. Cool. And I'm just going to roll it next to that so it's touching something. And then we will get a little, we'll put another thing under it to keep it from rolling this way. There we go, cool. So now we need these T handles here. So let's get a piece of, get a small piece of foil, cover that, and then 2 of these are going to come out. So we have these lifting handles for this purpose here. So these lifting handles give us a great place to grab onto. Actually, we're going to rotate that 90. So go ahead and get that covered. I see some fibers in there, and I certainly see some oil in there too, so that's going to be fun.
This is too big.
Nope, perfect.
Okay.
Just put it on.
Like,
yep.
Just like here?
Exactly, and then just kind of squish it in. Okay, screw this in where I just took the screw out from.
Sorry, what?
Screw that in right there.
Okay.
Now we're going to back these all out 1 turn. That's a half turn, 1 turn. 1 turn. So these are the alignment screws. 1 turn and 1 turn. So now take these 4 bolts out here. So take these 4 out. I'll take care of that. That was from the detector, so that's fine.
Okay. Sorry, can you point again to which ones?
That one, and then on the other side, same thing.
Okay. Take them out.
Yes, please. Actually, no, these were the aperture ones.
This one.
Yep, that one. Already got the cable free for that. And then let's see how the cables are set up for the rest. Okay, those 2 are also free. And we're putting some more zip ties on to mark what goes where. Yep, cool, you can put that in the tray for now.
What is that?
Somebody marked it with Sharpie.
Are you sure?
Yeah.
It looks shiny.
It's possible, or Sharpie or like fingernail polish or Loctites.
Okay.
It's pretty common to mark those ones.
Okay.
For like to know how many turns you've undone it.
Do you know how many turns?
Yeah, you've like done to take it off.
Mm-hmm.
So one of these air lines might hiss some, but the air compressor is shut off from the microscope, so yeah, it's gonna be this one.
It's gonna hiss.
Yep. Oh, I think the microscope, yeah, okay, the microscope's already basically been depressurized, is why it didn't hiss very much. So I got the nitrogen blow-off tool here. We're going to use this to blow some water out of our objective lens. So we're going to shut the objective lens isolation valve down here in the column. We're going to figure out which line is the inlet on the lens. Okay, so the one on the left is the inlet, so we're going to start with that one. We're going to take that line off, and then we're going to blow water in it so that we can get water flowing through the outlet. And then once we have the water flowed where we want, we're going to close off the valves that go to the microscope. Okay, so that should be more than enough to get our lens dry. So now we're going to shut all of our microscope valves. Okay, all of our microscope valves are shut, so water won't leak out. Take off our other fitting here. Oh, we lost the camera battery.
Maybe it's a sign. I've been streaming for too long.
Nah, this one dies quickly. Okay, we have, to get the rest of the column apart, we have 8 more bolts. Or no, we have 9 more bolts.
Okay. That's an
And then we'll
odd
call it
number.
that. We'll call it there.
Sounds good to me.
Cool.
This one I have to do by hand.
Can I have the driver?
Yeah.
Yeah, that one is in a really awkward spot.
Yeah, it doesn't really fit from either side.
So the next 4 are a lot easier because they're pointing up.
Mm-hmm.
And then actually the next 8 are a lot easier because they're all pointing up. So those are all pretty fast to get off.
Sounds good.
And then the one other thing we have to do to get the last part off, which is the objective lens. Do you want to reframe that camera?
Yeah, we're
Just kind of point out what or just kind of in the general direction of where I'm working and where you'll be working on that side. Yeah, perfect right there, horizontally. And then just a little bit more down would be great. A little bit more up, because we'll be kind of standing up some too.
how's this?
Great. Well, I'll be out of frame if I stand up. You want to zoom out some, or is it zoomed out?
I can zoom out a little.
Yeah, there we go.
Yeah, this is zoomed out all the way now.
Cool. Where were you putting all the other bolts? Right here?
Yeah.
Excellent.
I've been standing them up so they don't roll. All right,
Okay.
what am I doing with this? The next part?
You're gonna help me with this first. You're gonna manage this cable.
I'm ready to manage.
So I got our T handles in. Using our T handles, I'm gonna pull straight up. There we go. So that is the condenser lens, and this part is pretty heavy compared to a lot of the other ones. So just kind of be ready for that. And then because we pulled the condenser aperture out already, there's nothing that sticks down lower than the so.
It's
That is
time
great.
for me to drop tools and go.
Can we do the last 8 bolts, you think?
Are you seeing this monochroma?
So yeah, do you want to start on the far side, and I'll
Okay.
work in here. So now I get to do something in the sample chamber here. Yeah, that one.
This, and then 2 on that side.
Yep. comfort chiller is upset? Yeah, I turned you off. Or the chiller is like, you turned me off. And I was like, yes, I turned you off. That is as intended.
Are these interchangeable with the ones that we're pointing down?
They should be.
Okay, so I don't have to store them separately.
You do not. Good catch. Why did that come loose?
Because I shook everything. It's a sign.
I'm going to zip tie it to the microscope. I'm going to tape it to the microscope. I thought I had that wedged in there really well.
Maybe I shook it really well.
What?
Maybe I shook it really well.
That's possible.
Isn't it like missing a washer?
Yeah.
Yep.
Okay, the camera has been taped to the microscope. We'll put tape in one more spot. Okay, camera, I'm pushing on the camera and I can't get it to tip now, so. Okay, chat, we are almost done with this thing. And then Maria, once you have all those out,
Yeah.
actually no, that part's light, we don't need the T handles for it. I'm gonna take my specimen out.
Okay, I got them.
Okay, cool. Can you manage the cables on this one?
Yeah. But it should be on the same side as it, right? Or
Yeah. Actually, the cables are free on this one, so I just pull it up. Do you want to move to the side so the camera can see what we're doing?
yeah.
Actually, no. Go around back and manage the cables. Yeah.
Mixed instructions.
Optimizing, as iterating on the plan. These two.
Yeah, that's what I'm holding.
Cool. So that brass part. So what I'm holding right now is actually our stigmator and scan coil. So there is the stig and the scan. Can I zoom in on that? So stigmator you can see on the outside, and then scan's on the inside. Actually, wait. No, that's just scan on the outside there. Yeah, that's just scan. Cool. Oh, there's a little bit of, that's been dinged, but that's out of vacuum, so that's a pretty easy fix.
Okay, I'm dropping everything and going home.
Okay, sounds good. Well, chat, it's me and you for the last 2 parts here.
Good night, Monochroma. Good night, the rest of chat.
So this part's pretty easy. It's just 2 springs. It is sensitive though, so you want to get it right. So this is our backscatter detector here. We got to take this off the tip of the objective. We're going to disconnect our spring on the far side first.
Assuming this is the off button.
Yep. Oh, we lost a battery.
Do you need me to swap it?
That'd be great. Well, actually, you know, I got it real quick. You can get out of here.
Okay.
This will be done very shortly. Oh, my hands are so oily. Okay, actually, you know what? Yeah, can you get the battery out?
Yeah.
It's like, oh, I'm holding the objective lens. This is a clean thing. No, 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 no. Not on this microscope. Not clean on this microscope.
Okay. I got to...
Push on that part. Yep. Cool.
I don't know what that one is.
That one's charged.
Charged?
Yeah.
Okay. This one's not charged.
Can you put it back on the tripod, please?
Yep.
Completely forgot how oily our objective was. That's not a common experience, exactly.
Where do I tighten it? On the...
This side right there.
This one?
Yep.
That's what I thought. And then, it's not tightened. Okay, now it's tightened.
So. Okay, so we gotta go on the far side to get our spring off that side.
Do you want to zoom out here?
Yeah, go ahead. And then at the very bottom of the screen, can you set the, well, no, if you're zooming out, it's fine.
Like that, maybe?
Yeah.
What do you think?
Looks good to me.
Okay. Now good night for real.
Thank you so much for your help. And we'll see you.
I'm gonna turn this, I'm assuming this is off. If it's not off, then
Just put it in the charging case and I'll turn it off.
that was not off, that was recording. Where is the charging case?
Okay, so we're gonna pull the near side off first, and with the near side off, we'll be able to unhook the far side of our backscatter here. So we have the near side pulled off. Backscatter is loose. Hook or spring is out. And now we can get the spring off the far side. Okay, backscatter is free. So with our backscatter off, and some very oily gloves because of how dirty your chamber is, you can kind of see it dangling in there. We're going to put new gloves on, we're going to get our objective out, and that's where we're going to call it. Okay, so we got all of our cables are disconnected on that side. Our air lines are disconnected. Our tubes are disconnected. There's some spare screws down there that we didn't take out. Now all I gotta do is pull those 8 bolts out. Sorry, 4. And our objective is coming out, and we have got this column taken apart. So we got those 4 bolts out. And I see 2 small screws back there that are going to fall into our chamber if I pull this thing out and the position it's in. So we're going to move those out of the way. We got 1 and 2. Well, one's a washer, one's a very tiny screw. I wonder what this small screw was for. Okay, so we got all of our bolts out. We got our backscatter detector off. We need to unhook the cable from the backscatter detector that's attached up there. Okay, cable is unhooked. And there we go. So our backscatter is kind of still in the way there, so we're not going to push our stage in. I'm just going to get all of our cables up front before we start pulling it off. So this is all the cables that go into the objective lens. Certainly makes handling the objective lens interesting. Okay, here comes the lens. There we go, we got it out. So that is how you take a column off of a 6400. That is so oily, oh my God. That's wild. So we're going to store this one upside down because that's the most stable configuration for it. Then we're going to bring all of our cables over. And that is it. Well, chat, had a great time taking the scope apart with y'all. With that, Well, I'll give you all a close-up of this lens first, because oh man, is this thing just oil's caked on it. Actually, before I do that, I am going to get the backscatter detector secured into a safe stowage position, and then we can close the stage, cover some stuff with foil, and yeah, get into a good state. Basically, we're going to kind of zip tie the BSE to the secondary for now. And that keeps it up out of the way for the stage so that we can close the stage. Focus, please. Please. There we go. So that's the BSE zip tied to the secondary. This is what it looks like if you're an electron. POV, you're the electron. So we're going to cover the top where our column came out with some foil. And we can get our chamber closed. Oh wow, look at this hair. Look at this hair. I gotta show chat this hair. You see that hair there? It's a full-on cat hair. Look at that. Jeez, that's wild. And then we have somebody in the hallway who managed to lock themselves out of the lab. So I'm going to close the door in the chamber. I'm going to go let Maria back into the lab. I'm going to close the door in the chamber. We're going to wrap the stream up there. I'm going to go let Maria back into the... Well, first I'm going to take the hair out. Oh, that is... Okay, that is totally an animal hair. It's like black on one end, white on the other. That's great. I love that. So we're going to close the chamber. Chamber's closed. We're going to use the foil to kind of cover that more. We're going to put our hair in our test tube. We're going to cover our last port, and then we're going to go let Maria back in the lab. Oh. I think I lost the hair. Nope, it's still attached to me. Oh, it does not want to go in this test tube. It's being electrostatically repulsed from this tube. Okay, it is attached to the side of the tube. So that is our cat hair for analysis later. And we're going to put one more piece of foil on the scope, and then we're going to sign off. Thank you, everybody, for joining the stream. This has been a ton of fun. We'll get Maria to also sign off from the hallway. And then we will catch you all next time. Oh, okay, I got one more shot to give you. I promised you a view of the oily objective. I will deliver on the view of the oily objective. That is one oily objective. My gosh. Get a load of that. Wow. Just wow. Oil E objective. Okay, I'll cover those up once I'm back in. Oh, it doesn't even matter if I cover them because that's all being pulled apart and ultrasonicated. But with that, hey Maria, you want to sign off on the stream? Bye. Have a good night, everybody. We really appreciate you all for joining. I'm going to go let Maria back in, and you all have a good one. Peace. Bye. Where's the button? There's the button.